তুমি একটা সামনে চলে যাবো এরকম জায়গাতে এখান থেকে পেয়ে যাবো, এখান থেকে এই জিনিসটা বেশি বড় পেয়ে যাবো। ক্যামেরা
Welcome to all of you for assembling here, respected Maharaj, professors of our department, research scholars, and my fellow friends. Today we have assembled here in Ramakrishna Mission Vidyamandira for a conference on condensed matter physics, and here we will proceed on. And as a courtesy by Vidyamandira students, it is very customary for us to begin an event with Vedic chanting. So there will be Vedic chanting by 3 of our students.
तमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः। हरिः ॐ। भद्रं कर्णेभिः शृणुयामदेवाः, भद्रं पश्येमाक्षभिर्यजत्राः, स्थिरैरङ्गैः सुष्ठुवागंशस्तनूभिः वशेम देवहितं यदायु। स्वस्ति न इन्द्रो वृद्धस्रवाः, स्वस्ति न पूषा विश्ववेदाः, स्वस्ति नस्तार्क्ष्यो वरिष्ठनेमि, स्वस्ति न बृहस्पतिर्दधातु। ॐ शान्ति शान्ति शान्तिः। हरिः ॐ। पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते, पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते। ॐ शान्ति शान्ति शान्तिः। हरिः ॐ तत्सत्। श्रीरामकृष्णाय प्रणमस्तु।
That was indeed a very nice presentation. This shows how we students of Vidyamandira, along with working on science and technologies and modern affairs, have kept us afoot on our religious customs as well. Now, revered Principal Maharaj, Swami Shastragarananda, will address our guests.
Om Namo Bhagavate Sri Ramakrishnaaya. This is indeed very heartening to see that our physics department is organizing a day-long seminar on their chosen topic. On behalf of Vidyamandira family, institution Vidyamandira, and also on behalf of Department of Physics, I welcome all the dignitaries present on the dais and others in this conference hall. I am not a person of physics, so naturally it will not be possible for me to delineate on the different facets of the advanced age physics research. But as a common man, we can well understand the study and advancement in the subjects like physics, which is termed as a core one, always requires the deployment of young, energetic minds, brains, who will be able to cut through the new paths, the novel avenues of science research. Just other day, when we had a discussion amongst us on defining different matrices to determine the quality parameters of a higher education institute, especially a general degree college, we all were conscientious to point out to a particular decision that if our generation failed to bring new horizons, failed to usher in new lights on the horizons of basic science research, it will be difficult for the technological experts, the technocrats, to sustain the present day scientific revolution with which we are living, of which we are proud, and for which we are aspiring. It's very much true that today, all over India, better to say all over the world, people are trying always to relate science, its discoveries, its studies, with the need of the day. How does the scientific knowledge get translated into real day phenomena? It's really the demand of the hour. But if aiming at those, we only struggle to find out the placements, so-called placements, so-called startups, so-called industries, and so on and so forth. A time will come when we will see that we are lacking in grooming up some real scientific temperaments. What we need from our young students, young researchers, and the upcoming teachers is this, in short is this, that they should try always to innovate within themselves. Studying science or any subject at all is not only completing the syllabus or covering the curriculum and ultimately writing the answer scripts in the examination hall in a time-bound manner, but rather it should always target in innovating within our own mind to think of the things in a new way, to ask questions on every scribbling of the preceding scientists. If our students, our researchers, our teachers become able to put questions, raise debates, formulate different problems on their own, and start solving those on their own as well, then only the scientific study sees the sun of progress. Then only the scientific study gets established in the progressing avenues of human civilization. I fervently hope that today's seminar will not be a one-way show, will surely not be a single speaker display. Rather, it will enable our listeners, the audience, to create questions, to drop the debates, and to formulate new innovative arguments on their own. An argumentative individual can only add to the knowledge of human world. A seminar should always aim at nurturing the argumentative individual. If this seminar does so, then naturally it's the outcome for which we wait. Our physics department, teachers and students, all the invited guests, all the speakers and the participants, I do hope will try their level best to procure the best result, the highest outcome out of this interactive meeting, this scientific discussion. Thank you.
It was a very delightful lecture by our Principal Maharaj, and it clearly points out our vision that what we are expecting from this seminar. From here, I would like to call Dr. Bhavesh Roy, HOD of our Physics Department, to put an introductory remark of this seminar.
Good morning. Today we all present here to participate in the conference on condensed matter physics organized by the Department of Physics, Ramakrishna Mission Vidyamandira. This conference is a part of academic activities of our department. As we know, there are so many branches in physics such as relativity, optical physics, high energy or particle physics, nuclear physics, cosmology, string theory, condensed matter physics, etc. Besides those, the interdisciplinary fields are astrophysics, biophysics, medical physics, chemical physics, mathematical physics, econophysics, geophysics, and computational physics. So, what is condensed matter physics? The branch of physics where the physical property of matter in a condensed form is studied is known as condensed matter physics. The condensed matter physics appears whenever the number of constituents in a system is extremely large and their interaction between the constituents are very strong. The most familiar example of condensed matter phases are solid and liquids. The more exotic condensed phases are superconducting phase, plasmas, Bose-Einstein condensed. The study of condensed matter physics involves both in theoretically and experimentally. In experimental condensed matter physics, the physical properties are measured via different experimental techniques. The experimental data support the theoretical result. Theoretical condensed matter physics includes the basic laws of general physics like statistical mechanics, electromagnetism, and quantum mechanics. In theoretical study, mathematical models are developed by physicists that help us in understanding physical properties. One of such model is quantum computation. One of our invited speaker, Dr. Arnav Das, will talk about that topic. There is wide variety in the branch of condensed matter physics such as crystallography, elasticity, magnetism, metallurgy, etc. There is also the overlap with chemistry, material science, nanotechnology, electrical engineering, and relates closely to atomic physics and biophysics. Theoretical condensed matter physics shared important concept and method with that of the particle physics and nuclear physics also. It is the field in physics in which advances in theory can most directly be confronted with experimental data. Today, condensed matter physics is one of the most active and exciting research area in both basic science and technological applications. As the largest branch of physics, condensed matter physics has the greatest impact in our daily life. To have an understanding, the hearing is better than reading and seeing is better than hearing. A quote from Thakur Sri Ramakrishna. For a subject to have the initial idea, hearing is better than reading. In view of this outlook, we have arranged for hearing some aspect about the condensed matter physics. So we think it will be helpful to our student to take the decision in further study. Although to become a physicist or an academician, any of the branches of physics are equally important. But when the job is concerned or placement is concerned, it may be different. In this effort, we have with us two invited speakers, Dr. Arnav Das from ISCS, Indian Association Cultivation of Science, and Dr. Shantanu K. Maiti, Indian Statistical Institute, and other speakers. I am convinced that the presence of all, including our students and other participants, will contribute to the value of this conference. We can get a focus about which we are going to know from today's conference like that. Dr. Arnab Das will talk about quantum computation. Dr. Shantanu Maiti will talk about nanoelectronics. Basically, it depends on transport properties also. Dr. Asmi Haldar, many-body system. Dr. Amit Trivedi, antiferromagnetism in frustrated quantum system based on magnetism property of material. Dr. Surojit Guin, the quantum chemical structure and plasmonic properties. Dr. Somnath Bhattacharya will talk about the random register cum tunneling network model. So we can now start this conference.
Being mere undergraduate students, we could hardly cope up with the difficulty and the vastness of this subject. But yet, the way our dear professor has introduced us to these things and these matters of condensed matter physics, maybe it will be easier, much easier for us to understand. Now, there will be a felicitation where Professor Arnab Das will be gifted a token of gratitude from our Professor Rajesh Karmakar. Now another professor of our department, Dr. Sagar Vishwas, will give another token of gift.
Who will he give?
To Professor Shantanu Kumar Maiti from ISI Kolkata.
There will be the PowerPoint presentation. So we need to go there.
Now we proceed on to the next events. And now Professor Arnab Das from ICS Kolkata will give this who is invited here, will present his lecture, which is an elementary view to quantum computation and its analog version, quantum annealing. I will like to present shortly the academic profile of Professor Arnab Das. He is currently the Associate Professor of School of Physical Sciences, Indian Association of Cultivation of Science, Kolkata. Professor Arnab Das did his masters from Calcutta University in 2001 and obtained his PhD from Saha Institute of Nuclear Physics, Kolkata. Apart from this, he has held many postdoctoral positions in very renowned institutions like Abdus Salam ICTP in Italy, Los Alamos National Laboratory in Alamos, USA, and the Max Planck Institute for Physics of Complex Systems in Dresden, Germany. From now on, Professor Arnab Das will present his lecture on this topic.
To present one of this exciting topic, which was basically what I studied in my PhD days, and now my focus are a bit different, but still I think for the young people this is a topic which can be stated least technically and also can be very inspiring. So I thank Rajesh Karmakar, Professor Rajesh Karmakar, for particularly for this invitation. And this is a great place, of course, to be, given the heritage of our country, and the fact that actually Vivekananda was one of the most important proponent of doing basic sciences in our country. Of course, you all know that he was the mastermind behind this Indian Institute of Science, Bangalore, where he convinced Tata to give support to this institute. And also his influence was pivotal in forming the first scientific institute, this Indian Association for the Cultivation of Science, by Dr. Mahendra Sarkar. So naturally this is like a great place for doing science. I've tried to communicate some of the recent excitations to the students. The question is, what is quantum computation? This is the basic questions. Quantum computers. So what is a classical computer to begin with? A classical computer is blocks where you input bits, numbers in forms of bits, strings of bits, and it processes it according to some rule and output another string of bits. So let's call them X. X is a sequence of bits, and what a classical computer outputs is another sequence of bits which we call fx. It's a function of x, depends on x. And naturally these bits are represented physically by switches. So you can put a switch on and off, so it can be 0 or 1, and that's how a computer works. You have several switches to input your bits. Some of them are on, some of them are off, and then that realize a particular sequence of this 0, 1, 1, 0 kind of bit. So a switch, a classical switch, it can remain either or off. It cannot be in a state which is something in between. That doesn't work. It's a faulty switch if it's neither on nor off. So the idea of classical states are very specific to one of those on and off. This is not just for the switches, but also, as we will see, will be necessary later, it's true for particles. A particle can either be here or be there, a classical particle. It has a position x, momentum p, it can be a particular point in the phase space. It cannot be at the same time x1 and x2, at x1 and x2. That's not possible according to classical physics. So the concept of quantum computation departs from the classical computations right from this idea of states. So in quantum computer, you can have switches which can be in a state of superposition of both on and off at the same time. On and off, not on or off. So that's where it starts departing from the classical computation ideas. So it's quite drastic to begin with. So what do we gain? So as you see, instead of one particular x which you can input in a classical computer, you can input a superposition, linear superposition of several inputs together at the same time, simultaneously, in a quantum computer. Because the quantum computer switch allows you to do that. They can remain in a superposition of 0 and 1. And your quantum computer processes these superposed states, by which it means it acts on each of these elements of the superposition. That means each of these inputs excites simultaneously at the same time and gives you an output. So instead of calling these bits, they call it qubits, quantum bits. So this 0, 1 can be 0 or 1 or an arbitrary superposition of them. And the fact that a quantum device can simultaneously act on them by acting on a superposition of them is called quantum parallelism. So if there are n bits, there are 2 to the power n possible configurations of the string. each bit can be 0 or 1, so 2 into 2 into 2 n times 2 to the power n. And thus you have enormously rapidly increasing number of possible inputs. So if you have a string of 100 bits, it's 2 to the power 100, and if it's somehow 300, it's just beyond the capacity of any computer in the world within the lifetime of the universe to process all the inputs separately, one by one. 2 to the power 300 or 500 is an enormously large number. So there are problems where you really have to evaluate all possible inputs. For example, you want to compare different values of your function, fx, and find the least one. So in classical computer, there is no other way, unless you know specific nature of the function, but to evaluate each of the fx values for each of the input xi and then compare them. And if this number of bits in xi is 300, you are done. It takes a lifetime of the universe or even more. So, but this particular parallelism is implying that you don't have to do that. You take a quantum computer where your bits can be in superposition and your gate operations are represented by some unitary operators, which can be done. I'm not going into the details, but in principle, all possible gate operations can be represented. All possible means all necessary gate operations can be represented by unitary operators. So you replace your classical computer circuit by a set of unitary operators, and that's your quantum computer, and superpose all possible bits, all possible inputs together as your input, and then this unitary operator, as you know, it acts on u operating on a state psi a plus psi b is u psi a plus u psi b. So it simultaneously works on all of the 2 to the power 300 inputs at the same time and spits out the superposition of 2 to the power 300 outputs. So at the first sight it seems, oh, so basically all the problems of the world is solved, because now in one go you can do that. You don't have to wait till the lifetime of the universe, just one shot and you are done. But sadly that is not the case, because in the superposed output, the output is now a superposition of all your necessary inputs, and it's normalized. So strength of each input, each output in your output set, I mean the fxi's, each of them has an exponentially small weight. So again, weight of each of them are very, very weak. So it's basically, it contains all your answers, but all answers, there are all of them together, and each of them are barely discernible. They are very, very weak. So we are again back to the soup. We cannot read out anything basically from it, because if you do a measurement on the final step, you get your desired answer with a probability which is exponentially small again in the system size. So it's no better than classical computer. So do we get any advantage at all? That is the question. From the circuit point of view, actually there are only few. You have to design very clever algorithms, and then actually you can take advantage of this parallelism and in fact design algorithms which outperforms classical computers in principle by far. So there are two very famous ones. There are others also, but two of them became very famous. One is the Shor's algorithm, which can factorize a number which is very large, grows exponentially with the number of bits, So you have 10-digit numbers. The size of the number is 10 to the power 10. So 100-digit numbers is 10 to the power 100. So if you take the size of the number, then with the number of digits it grows exponentially. So factorizing it is considered to be a hard problem. So if you have a 300-digit number, there is no way you can try and factorize it in a normal computer. So that is also the basic idea of cryptography. So they give you one factor and they keep in their store as another factor, and when you multiply them you get the whole number. So and the whole number is given in the public domain. So but the difficult part is you cannot factorize it. So factorization is an important practical problem which doesn't have any efficient solution. Efficient means your time of evaluation should go polynomially with the number of bits. So actually quantum computer can do that in a polynomial time. So it's log in the number, in the size of the number, which is polynomial, basically polynomial in the number of digits. So that's a very famous one, and actually a pretty complicated one. And then another is a very interesting one, which is called Grover's algorithm. This was factorization was discovered by Peter Shor from Caltech, and Grover's algorithm was in fact discovered by an Indian, Love Grover, but he was in Bell Labs at the time. This problem is also very interesting. It says that suppose you have n number of completely random entries, like a telephone directory. So somebody asks you to find a particular number in a telephone directory, whether it matches with some name. And the directory is not organized. There is no alphabetical order or nothing. Like it's an unsorted database. So what you have to do, you have to visit every number and look up the name. If it matches, it matches. If it doesn't, you have to run to the entire directory. There is no go because the last name could be the name we wanted. So basically it takes the time which is on an average proportional to the size of the directory. So if there are n entries, your time scales as n. And there is no classical bypass because each of the entries are completely uncorrelated with each other. So knowing one entry doesn't help predicting the other entry. So you have to check every entry one by one. But like a magic, if you use this quantum computer, you can do it in square root of n trials. We will actually see eventually an analog version of this problem, which is also an interesting physical realization, and see how condensed matter ideas can come into play in solving these kind of problems. So before leaving this paradigm of circuit quantum computation and quantum parallelism, just let me demonstrate a very interesting toy problem, which actually where the power of quantum computation is manifested, and it's clearly understandable. It's not a complicated one like Shor's algorithm, pages of things, but it clearly shows how actually quantum computer might work. So the idea is there is a oracle. This is called an oracle. So what it does, it's a black box. So you give, it's a 1-bit oracle. So you input 0 or 1, and then it does a very complicated thing. I don't know what. Whatever it is, it does, it outputs again a single bit, 0 or 1. Now the question is, the problem is, this is called Deutsch problem. It's by David Deutsch in Cambridge. He said the problem is, you want to verify if the two outputs corresponding to two inputs are same, in which case the function will be called constant, or balanced. This will mean that two outputs are different in this case. But the classical answer is, of course, you have to operate the oracle twice, once on 0, once on 1, and get the outputs and then just check whether they match. So there are two uses of oracles, at least classical. You cannot bypass it. You can use two different oracles or one oracle twice, but it's a two use of oracles, of the oracle effects. But he formulated a very clever circuit which shows that quantum mechanics, you can do it just in one go. You don't have to use the oracle twice, you just use it once. The principle is, of course, this parallelism. You can act the oracle simultaneously on the superposition of 0 and 1 instead of just 1 or 0. You can act it at 1 and 0, which is a superposition. So here is the circuit. So you have two inputs, 0 and 1. And there, this is a unitary gate, which is basically like a Pauli matrix. I mean, it's not a Pauli matrix, it's a different matrix, but it's a 2 by 2 matrix, which does a unitary operation on this bit, and this does the same. This is called a Hadamard gate. So Hadamard gate, the action of Hadamard gate is defined in this. So if you put a 0, it puts it a superposition of 0 plus 1 by square root 2. If you put a 1, it puts it 0 minus 1 by square root 2. So that's what the gate does. So that defines the gate completely. And then there is a box, which is a super oracle. What does this box do? This takes this input from this Hadamard gate, calls it y, takes this one from, calls it x, and then he does just XOR. It's a two-bit thing, so just the standard Boolean XOR, and does nothing to this bit. This bit goes right through, and this line outputs y XOR fx. So it evaluates fx, and depending on fx, whatever the fx is, it XORs y with it and spits it out. That's state psi 2. So psi 1 is this one, 0, 1 going through two Hadamard gates, and then it might look a bit look like a bit clumsy, but if you just take a piece of paper and just do these Boolean steps, you will find how wonderful this is. And psi 2 is like this, this particular state. So what we note is if your x state is just x, whatever x it is, and your y state, this which is this one, is 0 minus 1, which it is, then what it does, it puts an overall phase of minus 1 to the power fx. How it does, you can just do a calculation and see, because if it's 0, it doesn't flip. It's 1. If it wants, then it flips, and etc. So then you see for this particular y, it just takes a minus 1 to the power fx out of the state and leaves the state out. So that is your psi 2. And if in case f0 equal to f1, which is balanced, then your psi 2 looks like this. And if f0 is not equal to f1, your psi 2 looks like that. So you already see there is a difference in sign that comes out to the first bit. The second bit is the same. So these two states are orthogonal, which can be easily seen if you put another Hadamard gate. It just gives 0 back, and it gives 1 back. So now your final state, depending on whether your f0 is equal to f1 or f0 not equal to f1, these bits are completely different to orthogonal states. So you just measure your first bit. If it is 0, you know f0 equal to f1, and if it's 1, you know f0 not equal to f1. And for that you just use the oracle once. You of course use it on a superposition of 0 and 1, but you just use it 1. So that's the power of quantum parallelism. So now we just drift to a more condensed matter setting of quantum computation, where people formulated this as an optimization problem. So what is an optimization problem? Basically you have many variables, several variables, and a function. Usually that is extremely complicated to evaluate and have, as I said, exponentially many possible outcomes. So it's not feasible to really evaluate every outcome and find the most optimal or minimal value of this function. So for sake of physicist setup, we call it Hamiltonian, this function, and these Jij's are couplings, and these sigma iz, sigma jz are bits. We call it Ising spins, which can also take two values, plus minus 1, and they are like bits. So it's completely classical because these are all sigma z. If you think even in terms of Pauli matrices, these are classical in the sense they all commute. So basically they represent a classical function. But these kind of problems can be extremely difficult to solve. If somebody asks for what configurations of sigma ij, sigma i's, these bits, this Hamiltonian has a minimum value. And complexity is enormous, at the same time importance is also enormous. in economics, in biological sciences like protein folding, in veterinary, it's like if you want to calculate the trajectory of something in a dynamic situations, this kind of optimization problem pops up everywhere. So there is no way you can really solve it exactly in most cases, because JIJs are completely random usually, and also they have different signs. If they were all positive, then the solution is easy. Each one has to be same, either all +1 or -1. Then that's the solution. But unfortunately, most of the cases, these GIJs have different signs, and that introduce what is called the frustration in the problem, and also randomness are always there in real problems. You don't find a problem where the distance between all the cities are same or something like that. So basically, the essential ingredients of a practical problem are difference in signs, varied signs of GIJ, and also random values. And that makes it a very difficult problem, typically known in physicist language the spin-glass problem. So intuitive reason, as I was saying, is randomness plus frustration. As I said, randomness is important because if everyone is equal, then it's a nice antiferromagnet or something like a ferromagnet, and you know what to do with it. And if the frustration is not there, then again it's an easy problem to work with, because you just have to align everyone in the same direction. So what typically happens in this kind of problems is the landscape. If you plot the landscape, maybe suppose you order the configurations in some order. The number of configurations, you order the configuration in some number, and here is the page. So this one I, particular I, represents an entire set of values for sigma 1, point represent one for this entire set. For example, then if you plot it, it will look extremely ragged like this. That means if you are here and you make some local changes in your values of speeds, you will be here, you will go here, up here. So you will know that energy is increasing. If you go this direction, you also see energy is increasing. So in every direction, one or two speed changes, you just see your energy is increasing. So that will give you an impression that you have reached a minimum. But actually, this is not a global minimum because there are energy barriers which is separating this minimum, and then there can be a far deeper minimum somewhere else. If it were like just one monotonic thing, then you can start here and easily reach here just by minimizing the energy. Just minimizing it, you reach here and you know that's the minimum. If there are several minimums,
Hello.
Hello? Yeah. So the idea is if there are several minima, then you don't know whether you are in the lowest minimum or not. So your problem is to minimize the energy to get the lowest minimum. You can get trapped here in a very, very high energy minimum. And then these barriers are very, very high. And so you try a little bit and you see that energy is only increasing. So you decide, okay, I've got this solution. And then there is another problem. This is the energetic part of the problem. And then there is an entropic part of this problem. What is that? Suppose there are few of these minimums, like 10 or hundreds, something like some number, or like something which grows with system size, n number of minimums, where n is the number of speeds. Then you can do different things. You can start with different initial states and try. And with some of these trials, you eventually find n minimals. And then you can compare n minimals. So it's a polynomial problem. But unfortunately for this kind of things where there are frustrations and disorder, the number of such minimums are also exponential in system size. So if you also try to do this minimization problem starting from different initial states, you will actually need an exponential number of trials again, because there are exponential number of minima. And then entropy kills you. You cannot do that. So these are roughly the ideas of doing this, getting the idea of how these difficulties can arise in this kind of problems. So one very interesting solution was proposed by a physicist, Ted Kirkpatrick, Thirumalai and some other people. They said, okay, look how nature minimizes things. Suppose you have a collection of atoms and molecules which can form crystals. They can also form very ugly, completely random structures. So if you take a melt the thing, and then rapidly cool it down, they will not get enough time to minimize their potential energy, and naturally their configurations will be very clumsy, ugly something, which is something here, something like that. If we call this free energy, then in some free energy, local free energy minima, they will get trapped. And your crystalline structure is perhaps somewhere here. So what do? You cool it very slowly. If you cool it slower, it gets more time, and then it has more scope to get over this minimum by thermal fluctuations. Because if it's hot, so it's not just looking for the low energies minimum, but there is a possibility to jump over the minimum, which is the Boltzmann factor. If this height is delta E, then there is a probability delta T beta. Beta is the inverse temperature. It's just not going down, but occasionally it also jumping over the maximum. So if you give enough time, it will jump over the relevant barriers and look for the entire landscape and find a very deep minimum. So that was the idea, which is called simulated annealing, and in the engineering, this is the technique to find optimization problems, because there is none other. So how do you introduce temperature? You do nothing. You just take this Hamiltonian and pretend that there is some temperature beta, inverse temperature beta, some temperature T. You take it very high in the beginning. So basically, you have all the states looks like almost equally probable, because potential energy is now scaled by temperature, and that's negligible, it's almost 1. So you jump over, and then you slowly reduce the temperature. Then it will not go out of very deep minima, but go out of shallow minima. And then you do it slowly down, and then eventually there is a possibility that you will find a very deep minima. Certainly there is no guarantee that you will get the most deep minima. There is a guarantee about that. It's called a theorem by Gaiman and Gaiman. But that said, you have to do it extremely slowly. You should wait infinite time, and then of course you get the lowest minima, but that's not very useful. What's useful is you can get a very deep minima, which is a good approximation to your final state by this method, in general. But the problem arose because, in this kind of spin-glass scenario where you have frustration and disorder, this height of the things also grows in system size. This height grows in system size. The barrier height is different. That makes your delta E proportional to n. Which means your jumping probability is again exponentially suppressed by system size. So then again you are trapped, and it will take exponentially long time in system size to go out of these barriers. So this is the problem in simulated annealing. And then came a solution from the quantum mechanical side, which says that, look, if your barrier is very thin, but high, which is often the case, then one can use quantum tunneling. Because quantum tunneling not only sees the height of the barrier, thermal jumping just sees the height of the barrier. It doesn't see how thin it is. But quantum tunneling actually sees both the height and the width of the barrier. So if the width is very small, then there is a higher probability to tunnel through. And in case the barrier is very narrow but quite high, there is a higher probability for the system to tunnel through. So this is true for particles. This is easily shown for particles. And then Professor Vikas Chakraborty of Shah Institute in 1989 made a drastic proposition that this is also true when there are many particles and your wave functions are actually many body wave functions. That's a very, very drastic assumption, and they did some simulation to show that in certain spin class it actually works. That's a debated thing, but the entire idea was that. So with all these intuitive ideas came a little bit more rigorous formulation of this optimization problem using quantum annealing. But for that we just revisit what is called the adiabatic theorem of quantum mechanics, which says that suppose you have a Hamiltonian which is dependent on time, and your instantaneous wave functions, I mean the eigenfunctions are these, they are invalid, and you want to change this Hamiltonian time. And the question what this theorem basically addresses is what is the probability that the system remains, if it starts with one of its eigenstate at time t, so it remains in that particular eigenstate all the time. So suppose it starts from the ground state, it stays to the ground state all the time. What is the probability? So the rate of change of this particular coefficient, which basically says how much is the weight of your particular time-dependent eigenstate in your time-dependent wave function, has this particular form. It says it depends on the instantaneous gap between a state k and n and this matrix element, which says which determines the rate of changing of this particular ak due to the presence of a level n. So that's basically say how much of your how much is the probability of you staying in a level k instantaneously go to a level n is given by this guy. And if this is very, very small, that means your gap has to be very large and this matrix element has to be small, then basically there is no transition. So you can start with the ground state and go to the ground state. Based on that, Adwak and Ishimori and later Fari et al. proposed a very beautiful scheme. So like, look, you have a classical complicated Hamiltonian whose velocity low. You put a strong quantum Hamiltonian which does not commute with it. How much time do you have? Battery down. Yeah, so the idea was you take a classical Hamiltonian whose ground state you want to find out but you don't know, and then take another Hamiltonian which does not commute with it. If you do that, this Hamiltonian, now the ground state of the total Hamiltonian is neither the ground state of this guy nor the ground state of that guy. But if this guy is 0 and this is 1, then of course the ground state at t equal to 0, you tune these Hamiltonians, both the Hamiltonians following the schedule. So t into t evolution, it's revolution time, and 1 minus t by t evolution into hq. So at t equal to 0, basically you start with this quantum Hamiltonian which does not commute with the classical Hamiltonian. Hence, the ground state of this Hamiltonian is basically a superposition of all the configurations of this classical Hamiltonian. So you basically start with a superposition of all the classical configurations, which is the ground state of this one. And then slowly, like as you tune temperature, slowly tune this particular strength of this quantum Hamiltonian down. And eventually, after t evolution, this strength becomes 0. You are left with only the classical Hamiltonian. And if you can do it adiabatically, that is very, very slowly, then adiabatic theorem of quantum mechanics says that you started with the ground state of your total Hamiltonian, which was the ground state of h cube, And now you have ended up with HC, which is now the total Hamiltonian of the T evolve. So your ground state, your final wave function will be actually at the ground state of HC, because that is the total Hamiltonian of T evolution. So this is called the adiabatic quantum annealing, but there are of course problems with that. We are coming to that. So if there is a question, you can just ask now, if the protocol is clear. So you start with this Hamiltonian and slowly tune it down and tune this up. So this is Hamiltonian whose ground state you want to know. So the total in the total Hamiltonian, the weight of this guy goes down this side, and weight of this guy goes up. So adiabatic theorem of quantum mechanics says that if you start with the ground state of this guy, then finally you will get if you do it adiabatically very slowly, then all the time your Hamiltonian will be the ground state of the total Hamiltonian. At the end, the total Hamiltonian is nothing but your classical Hamiltonian, so you are expected to get your wave function at the ground state of the classical Hamiltonian. So that is how this introduces what is called the quantum fluctuations, because its ground state is basically a superposition of all possible classical configurations. So you start with a parallelism already, and your Hamiltonian is now your quantum circuit. It basically processing all the classical states, superposition of it, and as you evolve, it's working on it and eventually filtering out the classical ground state which you want to find. So the question is, what are the difficulties and pros and cons of this problem? We are coming to see those. So start with the most simple problem. Suppose you have a fine table. It's as I said, it's a analog of Grover's algorithm. So you have a fine flat table, completely flat table, and somewhere on the table there is a hole. And you set a classical walker free to find the hole. So what will be the time taken by the walker? It will be proportional to the surface of the table, right? Because he doesn't know where the hole is, and unless he really falls into the hole, he doesn't know where the hole is. He might just visit the next point to the hole and then skip the hole and go to some other point, because it's completely flat, there is no gradient. So this is a purely entropic problem, there is no energy barrier. So question is what a quantum walker would do. You can take as a quantum walker a quantum particle which starts from a state which is completely delocalized over the entire table. So from the very first initial time, he knows the entire landscape of the entire table, and as you reduce the kinetic energy of the particle and ramp up the potential energy of the particle, this is just the same scheme as I described before. So initially there was no potential energy. Potential energy is hc, which you tune to 0, and hq is your momentum term in the Hamiltonian, so it's a plane wave over the entire table. So it sees the entire table at the same time. And now you are tuning the potential energy up and reducing the kinetic energy down, and then the potential is appearing, and the particle at the same time, since it's delocalized over the entire table, it can really sense, okay, so there is a potential energy hole growing with time. But it is sensing it all the time, not it has to wait until it really falls there. So does it have any advantage? So eventually when you just tune the kinetic energy down, it's just the potential energy part in the Hamiltonian, which is the hole, and the particle is supposed to be localized there. So yes, of course, because this is a abstract version of this problem where HC is the projector on this hole, and H, I, J are the hopping term between all the different other sites. What it has been shown in this paper that, in fact, if your hole is deep enough, your hole size is proportional to the size of the table, then it takes off order 1 time. That means it doesn't depend on the table size. But in the classical case, you make the hole however deep. It doesn't matter, because unless the particle really finds the hole, it doesn't know the depth of the hole. But the quantum particle knows the depth of the hole from the very beginning, because it's delocalized over the entire table all the time. So that makes it possible that it utilizes the depth of the hole as one of the parameters of optimization and really converges to the solution in a time which is independent of the table size. In the classical mechanics, this is not possible. Classical mechanics, this problem is always proportional to the table size, irrespective of the depth of the hole. So this is basically Grover's search algorithm, because all the points in the tables are uncorrelated because it's a flat table. Going somewhere you don't know where the hole is doesn't help. So it's like an unstructured database. And what you are, and this is a quantum annealing version of this unstructured database problem, Grover's problem. And as I showed, you can manipulate the time scale of the problem by changing the depth of the hole, which is completely absent in the classical scenario. So there are also other interesting results which came up eventually. So this is like some Edwards Anderson class. I'm not going to go to it. Some kind of this Hamiltonian, one particular version of it. And this is, they have these ZZ interactions, and they have this quantum Hamiltonian, which is the sum over I sigma Ix. The ground state of this guy is basically superposition of all of these classical configurations. And they showed that if you just do quantum annealing, classical annealing, this reaches you here. This is in the log scale. And if you do quantum annealing, it goes to much deeper in the log scale, as you see, quite a few decades. And a simulated annealing, if you extrapolate, would take to go there like 400 years, which they did in two hours or something. Of course, they didn't do it in a quantum computer. They could not do that. They did it in a real computer. They simulated what is called quantum Monte Carlo, but they kept the quantum mechanical tunneling part in this. So this is not even a quantum computer. This is just a classical computer, but they, instead of just tuning the temperature, they also tuning the transverse field, and then they did a mapping from the classical to quantum, and then they did the simulation. So that was very inspiring, and many people thought, okay, so we have entered a completely new era of technologies. And then there were interesting developments from NASA and other places. We did a very simple-minded example of how quantum tunneling can help. And eventually in a NASA's technical report, it came out that this particular model somehow helps in navigating in the space robotics. We don't know how, because they don't disclose this. It's a classified thing, but they wrote a technical report where our entire things came with figures. This was very surprising because this model was completely of academic interest. We never thought that it will be of any practical use, but somehow it seems that in some corner of the world they have some practical implementations and utility. So that's the point which was stressed. So when you do basic science, you might just forget where it will be utilized. Just perceive this something very intriguing, and at some point of time, some technocrat people will find some application. So this is just a recent development page. So there is a company in Canada called D-Wave. They claim they can make a quantum annealer. With hundreds and thousands of qubits. And then it immediately came to BBC and all other kinds of media, and then Scientific Americans, and then European Physical Journal asked me to conduct a scientific review on this topic. So this is a book where all these people who worked on this project actually contributed some article. I edited with some Japanese friends of mine. So what turned out that actually this is not a real quantum computer. This is basically a quantum computer with 6 qubits and a coupling of those. So it's not a 1000 qubit quantum computer, it's just a 6 qubit quantum computers put together. And the coupling between these 6 qubit quantum computers are completely classical. So whatever it does is not really quantum computation, but maybe something which is close to quantum computation, but not exactly. And as I said, that one of the most deterring thing is the small gap from adiabatic quantum mechanics, adiabatic theorem of quantum mechanics. We show that the probability excitations goes as inverse of gap square. Gap means the gap between the ground state and the excited states. And then there is the famous problem of localization, which means that if you have disorder, your wave function particle tends to localize in one of the minimas, and it doesn't see the other more deeper minima unless they have resonances. So this again leads to an exponential slowing down of this quantum annealing kind of protocols from a completely different reason. This is a quantum mechanical reason, it's a superposition thing. So in generic problems with disorder, there is again this exponential separation of quantum advantage. Yeah, so I kept it blank because I thought I would write in the board, but just let me tell you some verbally. So if you have a ferromagnet, complete ferromagnet, just bonds are disordered, you know what the ground state is. Doesn't matter what the value of the bond, each guy is telling the next guy to line in the same direction. So if you put everyone in the same direction, that's the lowest energy, if all the signs of all the things are positive. But even that problem becomes exponentially difficult because of the disorder and localization in quantum annealing scenario. So while quantum annealing seems to have advantages, as I showed in many problems, even practical importance, they are not a cure of everything. You cannot cure all, and then people are trying to understand what are the basic bottlenecks other than this, and which are the areas where this can be helpful. So one main problem is find a suitable problem. As you can see, it's not general solution to everything. So there has to be a very acute, minute lookout for problems which are important, at the same time can be solved faster using quantum annealing. So the finding of problems is one problem. Another is decoherence, because you have to maintain the wave function in a superposition state that's very difficult to sustain in real systems because of the environmental decoherence. It immediately projects it out and decoheres into a classical mixture in a mixed state. But you have to keep the wave function in the pure state, which is a very difficult problem. And another problem is the quantum mechanical systems, which actually can realize these things like NMR, etc. Those things are not scalable. You cannot make many qubits out of that. The systems which are scalable are not so much resistant to decoherence like superconducting qubits, etc. So this is roughly the scenario of this field. On this matter, people are trying to find suitable structures, suitable computational hardwares where these things can be implemented. And quantum computational theoretical sides, people are trying to find algorithms which will be useful to solve some important problem which you cannot solve in classical computers. So thanks for your attention. This is our institute, which was established in 1876. It's the first Indian Institute of Science of the time. Actually, the first Indian Institute of Science. And this is the spectrometer which Raman actually used in this institute, not this building, it was somewhere else, to find the first Raman spectrum. Okay, so thanks.
I will ask students to ask some questions if they have on the topic. Anybody? Anybody with some query?
So either the top was very good or it was extremely bad. It cannot be something in between. Okay, let us thank for it.
The next set of events will be a technical session, will be chaired by Professor Shantanu Kumar Maiti, I like to bring you on stage. The speaker for this session is Osmi Haldar from IACS Kolkata.
Okay. Yeah. Okay, so good afternoon all. It's indeed a great pleasure to be here at the session. So in this so there is only one lecture in this technical session. It will be delivered by Osmi Haldar from Cultivation of Science. So how much time? 20 minutes. 20 minutes. So I should try to finish.
So thanks the organizers for giving me this opportunity to present some of my work here. So I'll be talking about the absence of thermalization in periodically driven interacting quantum systems. This work is done in collaboration with my supervisor Professor Arnav Dash and Professor Roderick Meissner and Professor Vidyamandira. So the central question of this work is so let's set up the platform first. So the central question is what happens if you drive a closed quantum many-body system periodically. So if the Hamiltonian at different time doesn't commute with itself, so that means there is no trivial conservation. So the system either absorbs energy from the drive without any bound or stabilizes to a new drive-dependent steady state by quantum interference depending on the Hamiltonian. So let us set the basic ground of the periodically driven many-body systems, which is the Floquet picture. So if you have a time periodic Hamiltonian H, which is time periodic in capital T, and the time evolution operator corresponding to that is U, given by U. So that operated on state psi 0 takes it to the state psi t. So you can define effective Hamiltonian H effective for that unitary operator, which is given by this e to the power minus I H effective tau over one single period. And if you observe after this time period capital T, which is called the stroboscopic observation, so your final wave function is given by this psi nt is equal to e to the power minus I H effective tau or t on psi 0. So the time evolution due to the time dependent Hamiltonian is effectively given by this time independent Hamiltonian H effective till time nt. And the eigenstates of this effective Hamiltonian, which are called the Floquet eigenstates, play the same role as played by the energy eigenstates of a time independent drive Hamiltonian in a quench, provided we observe it stroboscopically. Stroboscopically means if we observe after just time period t. So we introduce the Floquet diagonal ensemble, which is necessary for the next few slides. So if we represent the Floquet eigenstates as mu I, so any initial state, size 0 can be written as a linear combination of these Floquet eigenstates, because these Floquet eigenstates forms a complete basis, and any local operator is given by as at a very long time, n tends to infinity. The limit of this on the expectation value of this any local operator can be given by this. So for a very long time, these the off-diagonal terms are do not contribute, and basically they cancels out with each other, and only the diagonal terms remains. So this kind of a term will remain, so which is equivalent to a diagonal ensemble average over this some diagonal ensemble average. So what happens if you drive a non-interacting many particle system periodically? It goes to a generalized periodic Gibbs ensemble, and if you drive a many body system with interaction in presence of some disorder, it goes to a Floquet MBL kind of a system. Now another scenario is when if you take a many particle system with interaction without disorder and drive it periodically, it was known that it goes to a featureless infinite temperature like ensemble. So our question is, in this work, our question was that is there any interesting Floquet phases in interacting systems at any regime? So what we got, the answer is yes. So there is a KAM like which is a CAM like scenario. So interesting phases can be observed below a threshold strength of interaction compared to the drive strength. So to show that, we take this interacting spin Hamiltonian. So this is the nearest neighbor interaction. This is the next nearest neighbor interaction, which breaks the integrability of the model. And this is a longitudinal field, and this is the transverse field. So you drive the, and there is this drive part. So the drive is, so you drive the longitudinal field periodically. The drive is like square kind of a pulse. So for half time of the period, it's plus hx, the drive amplitude is plus hxt, and the other half of the period it's minus hxt. So what happens if this drive amplitude hxd is low, and your initial state, so in your initial state is, so since you're starting with plus hxd, so your initial state is quite highly magnetized, so its magnetization is nearly +1, and as you switch on the drive, if the drive amplitude is low, the magnetization goes to 0 very rapidly with time. And if your drive amplitude hxd is quite large, it remains frozen to the initial magnetization at 1. So here are the results. So this is the magnetization, the diagonal ensemble average of the magnetization, which is the infinite time limit of the magnetization, and this is the drive amplitude, and these are the different system sizes. So you see that there is a threshold region where for the drive amplitude where the magnetization goes to 0, showing that it's nearly thermalized, and after that threshold the magnetization remains close to 1, that is frozen to its initial state. And this is the system size dependence of the magnetization. for the large drive amplitudes. Which shows that as you go up in the system size, the magnetization becomes higher. And this shows the time average, long time average, and the diagonal ensemble average of the magnetization. Which matches quite well. That means that which matches quite well. So this is the same plot, just plotted as 1 minus mx as a function of the drive amplitude, which shows that the threshold does not move from this particular point with the different system sizes. So, and here is the transition point, and for the different system sizes, all the curves just meet here, which is the transition point. This is for different transverse field. Transverse field is the term which breaks the integrability of the Hamiltonian. So depending on the transverse field, the threshold is broadened or shortened like this. So here we measure the inverse participation ratio of the Floquet eigenstates. So mu I are the Floquet eigenstates and x are the longitudinal basis states. So inverse participation ratio is defined like this, which tells you how localized or delocalized the particular state is in that particular basis. Here it is the longitudinal basis. So you see that for small drive amplitudes, the Floquet states are quite, the IPR is nearly 0, which means that the Floquet states are quite delocalized in the Hilbert space. But for a large drive amplitude, a certain kind of a structure appears, which means that the Floquet eigenstates are quite localized in the Hilbert space, and this is the system size dependence of the Floquet eigenstates. The IPR of the Floquet eigenstates for a particular drive amplitude. This is the magnetization of the Floquet eigenstates as a function of the Hilbert space dimension. And the black line is the magnetization of the longitudinal eigenstates. So the Floquet states and the X basis states have one-to-one correspondence in the magnetization values, which means that there are mixing in the there are mixing in the Floquet eigenstates, but within the same magnetization sector. So the drive does not mix the eigenstates from the different magnetization sectors. So that shows that magnetization emerges as a quasi-conserved quantities. In forming the Floquet basis, X basis states form different magnetization almost do not mix. The dynamics approximately conserves the mix. So here we show the robustness of this freezing phenomena. So our initial, in the previous cases, our initial state was the ground state of the initial Hamiltonian. Here we take any random state but slightly polarized in the initial state, but slightly polarized, and we see that the same phenomena remains, and that is there is a threshold, and after that the states are quite frozen to its initial magnetization. Also, we can divide the time period as not differently from half and half. in that case also the freezing phenomena remains. So this is the dependence of the phenomena on the different drive frequencies. So this is the phenomena is quite robust on the different drive frequencies too, but for a very large drive frequency the freezing goes down. So which shows that this freezing phenomena is particularly low frequency phenomena which cannot be explained by the Magnus expansion kind of high frequency expansion thing. So here is the conclusion of my talk. Strong evidence against the myth of interacting flow case state always heating up to infinite temperature like state has been presented. This opens up a new possibility that that of stable flow case engineering in interacting systems. Stable flow case time crystals without disorder or dissipation cannot be ruled out in view of this. An analytical proof of absence of heating in interacting flow case system emerges as a holy grail. So thank you for your attention.
Do you have any question? Okay, so let us thank the speaker once again.
Now it is time for lunch break. After a 1 hour interval, we will resume the series of events, which will be preceded by a second technical session chaired by Arnab Das. For now, it is lunch break until 2:30. Our day-long seminar. For now, Professor Santanu Kumar Maiti from ISI Kolkata will give his lecture on molecules, basic building blocks of nanoelectronics. This will be later followed by a technical session which will be led by Professor Arnab Das.
Okay, thank you for the introduction, and first I would like to acknowledge the organizers for inviting me to deliver a lecture in this program. Today I will talk about some important aspects of electron transport at molecular scale level. So before going to the detailed analysis, let us start with a very simple experimental result. Suppose you have a two-dimensional conductor having dimensions, say L and W. Okay. So now if I ask you what will be the expression of electrical conductance, you all know. It's very simple. It can be written as this one. Right? So sigma is the electrical conductivity and it's independent of the dimension, basically is the material property. So this is a well-known and very simple result. Now the point is that if you reduce this W, right? Suppose if you reduce this to 0, then from this expression we can see that it will eventually drop to 0, right? According to this prescription. But the experimental results suggest completely opposite scenario. Okay, so now I can simplify this result in this way. Suppose you have a single energy channel, This is an important point. Single energy channel or single energy mode through which electron can transfer from this side to that side. So you have enough number of electrons in this side. Electrons will eventually pass from this end to that end. We call it as source, and this is the drain end. So what experimentalists suggest that if you have such a simple single mode energy level, so eventually you can think about this system where W almost tends to 0, basically W tends to 0, this is a one-dimensional case. Then this G is no longer 0, rather it becomes a simple 1. All are in terms of fundamental constant. Right? You know the meaning of E and H is a Planck constant. And if you consider spin degeneracy, this conductance will be simply multiplied by this factor. Now from this expression you can see that for the case of W equal to 0, it goes to 0. But this is the experimental result. And now if you take the inverse of this, you will get the resistance, as simple as that. So what will be the value of that resistance? Just you have to write H by 2 square. If you substitute the values of E and H, the resistance is roughly see how much this 12.9, almost 13 kilo.
Doesn't depend on air?
No, this one I have already considered this ballistic one, single mode, perfectly ballistic. There is no scattering inside the channel. Okay. So now
It's like within the military bar.
yeah. So it's just, you can imagine 13 almost kilo. Okay. So what is the physical explanation? Means from where we can expect this resistance. Now we can explain it. Say this is the source. This is a perfect material. You can think about these two ends just like the two ends of the battery. And you have a single energy channel. Now there are enough number of electrons, say for example 1000 electrons, and only one electron can pass through this. So that means there is a big traffic in this point. So due to this, we have this resistance, and that's why it is called contact resistance. Right? But normally, whenever we do any experiment in our say, graduate or undergraduate course, we don't bother anything about this contact resistance. Okay? So what is the physical explanation of that? Now, if we increase the width of the sample, that means if we consider multi-moded sample, so that means the scenario will be like this. You have enough energy levels, then you can write this one is multiplied by this number of modes n. So if you take the inverse, basically proportional to this one, right? So if you have a finite width sample or multi-moded sample, due to this large n, eventually this contact resistance drops to 0. So in that case, we don't have to bother about this contact resistance. So now, the question is that if we reduce the dimension after a certain length scale, the first question is that is the ohmic relation valid or not? So the point is that how small can we make the dimension before the ohmic nature breaks down, right? And there is a specific name, we call it a mesoscopic regime or mesoscopic physics. Mesoscopic means, what is the name? Means meso, means in between, micro and macro. But of course there is specific definition of this one, and how to characterize this mesoscale system. There should be some length scale with respect to which we can define this one. So normally we define three important length scales. You can imagine the dimensions of this, just of the order of say the millimeter, nanometer in one case, and the third one is the phase coherence length. And this phase coherence length, this is the most important one, That means the length scale over which an electron preserves its phase number. I will come to that once again. Now this factor, means this phase coherence length, here it depends on different physical quantities. For example, the simplest one means what are the responsible factors that can destroy this coherence length. One important quantity is the electron-electron interaction, Coulomb repulsion. Another is electron-phonon interaction, that means associated with the temperature. Now for one-dimensional case, if you calculate this, you can show that roughly it is inversely proportional to absolute temperature, roughly, not exactly. So it means that if you reduce the temperature, L5 will increase, and eventually at absolute zero temperature, mathematically you can have a infinite 1D, and you can say that okay, it's under this coherence regime. And there are other some important length scale. I will not describe those length scale. Now several important phenomena can be observed in that particular regime, that is the mesoscopic regime. Today I will highlight some of those. So one thing what we have already understood, that if we reduce the sample size, means if we go into this micro scale level, then your definition of resistance should be different compared to the conventional definition. Okay? And how to describe the transport phenomena in this small scale system. Okay, so now I just want to highlight one important aspect first, that is a circular current in a quantum loop. Okay, suppose you have a simple ring geometry like this, and it is metallic ring. This is most important. This is the metallic ring, okay? Not superconducting ring. Simple metallic ring. So what will be the charge carriers? Just free electrons, right? So now in absence of any, say, magnetic field or electric field or whatever, you cannot expect any response here, because there is nothing, no externally driving anything, right? So this is because of the fact that, say, think about the current. So if you have the probability of getting, say, electron in this direction, it will be exactly opposite, the same in the opposite direction, because there is no external field, nothing. Now, if we apply, or if we pass a very thin solenoid through this, very thin, and mathematically say if it is infinite, then you know, so the scheme is like this. We have to pass a very thin solenoid through this, and if it is infinite, say for example, then you know that magnetic field outside the solenoid is zero, right? It is confined within this region. And again you can think that okay, since there is no magnetic field outside anywhere, so we cannot expect any response, right? Because the magnetic field doesn't penetrate the ring circumference anywhere. So this is the geometry, just you pass a thin solenoid through this. Now if you allow a current through the solenoid and then suddenly drop it, then you will see that a net current will be established in the ring. And the most important thing is that if you switch off this current will never drop to zero, even in presence of disorder. I will come to the mechanism. So that's why it is called non-decaying circular current, and we are talking about only charge current, so it is non-decaying circular charge current. That is the persistent current in normal metal ring. Now, analogous to this persistent charge current, you can also see if you have a superconducting ring. There also you can see persistent current, but the mechanism is completely different. In that case, charge carrier Cooper pairs, not free electrons, right? So what is happening here? In presence of, say, this magnetic field, and this magnetic field doesn't penetrate the circumference of the ring anywhere. You know that B is zero, it's fine, but this curl of A has some non-local effect, that is a vector potential, okay? And if you have a, say, path like this, say this is 1, and this is point 2, an electron say moves from this 1 to 2 in presence of non-zero vector potential, it will occur a phase. If you go through the Kittel's book, the last chapter we will see that. So what will be this phase factor? This phase, it can be written as E by CH bar 1 to 2, a simple one. So that means so one full rotation, what will be the phase? So you have to do this. Can you see this? So E by CH bar A dot dl, right? So you can write it curl A dot ds, that means B dot ds. So it will be E by CH bar times your magnetic flux phi. Huh? And what is this? E phi CH. So you can take this E in the denominator, it will be this. And what is this quantity? CH by E. You all know this one, CH by E. It's the flux quantum, phi 0. So magnetic flux phi is measured in unit of this. So total phase that is acquired by an electron for this complete rotation by this. Now due to this phase factor, the probability of getting electron in this direction, it will be different in the opposite direction. That's why, so there's a nice name, it's called the breaking of time reversal symmetry. In presence of this non-zero vector potential, a net circular current will appear. Okay, and to get this phenomenon, you have to restrict that this coherence length at least greater than the dimension of the ring. So this is one important phenomenon that is observed in this small scale system in presence of this magnetic field. Now think about this same problem, but I will connect. So it was an earlier problem. I will connect it with two electrodes, that means two ends of the current, source and drain. So now it's known as open quantum system. So electrons are coming from this side, and there are two possible paths, this one and that one. So they will reunite here, eventually they will transfer, right? So again, for this case, you can write the conductance, electrical conductance. So what will be the scenario? Means if I calculate conductance, what will be your expectation? It will increase with phi, or it will decrease with phi, or it will be constant. So you can calculate conductance G, and it can be written as some constant G0 plus G0 times cosine by this. Cosine twice pi. So that means conductance will oscillate as a function of magnetic flux pi. It is no longer constant. And two famous scientists discovered this. So it is Arnav and Bohm. That's why it is called AB effect. So conductance will oscillate as a function of phi. Now from this expression, you can see that when phi equal to phi 0 by 2, that means half flux quantum, your conductance will be exactly 0. So that means complete destructive interference. So no electron can transfer from one side to other. And you will get this expression only under the condition when these two arms are symmetric, lengthwise symmetric and status wise also symmetric. Okay, that means same identical atoms, same atoms here. So in this condition, you will get G equal to 0, completely destructive interference when phi is set to phi 0 by 2. Right? Now, you can utilize this result in different ways. How? Just I'll give you one example. So our geometry is like this. We have a flux which is fixed at phi 0 by 2. It is connected with source and it is connected with drain. And the upper and lower arms are symmetric. So that you will get this complete destructive potential. Now I have say 2 electrodes through which I can apply the voltage. So like I have one electrode here, another electrode here, and say I can call it say VA and VB. Okay? And locally we can tune the site energy at a particular site. It is possible by applying 2 gate electrodes. Okay? So now think about the situation. Suppose you have one input, this is another input, and say this is your, I will calculate the response and the drainage. Now when there is no signal in both these 2 electrodes, both are 0, so of course you will get 0 response there because this lengthwise symmetry. So you will have this one. Because I have already set phi equal to phi 0 by 2. Now, if you apply a voltage there, suppose this is 1 and this is 0, now the symmetry is broken, right? Upper and lower arms are no longer identical. So we will get a non-zero response. So it will be like this. Clear? Similarly, we can think about a situation where this is 0 and this is 1. Again we will get the signal in the right end, drain end. And now when both the inputs are on, that means again these 2 arms are lengthwise symmetric. So we will get 0. Is it clear? I think you are familiar with this table, right? It's the logical response. And this one. Clear? Very simple. Just. What happened? Clear? So it is possible only if we apply a flux phi 0 by 2, half flux quantum, and if it is lengthwise symmetric from this relation, you see that it is exactly 0. So we have to break the symmetry at different points. Okay. So this is one prescription to get this logical response. Now there are several other propositions how to get different kinds of, in fact all possible logical operations can be performed by using this simple AB effect. Drain it. This one means I will calculate the current here. So electrons are coming from this side. There are 2 possible paths. This one and that one, they will reunite. So I will measure the current here. So under this condition, there will be no current there because complete destructive interference, this one, right? If you break the symmetry, you will get a finite response. So just by applying a gate voltage here, so that means if you change the site energy here, these 2 arms no longer identical. So that you will find a net response. Similarly in this way, you will get another response. And again, if you apply signal at both the 2 points, so these 2 arms will be symmetric, you will get this one. So this is the simplest way of getting logical operation, just considering simple normal metals, no semiconducting material, nothing, and it's very small. Okay? Now, up to this, what I discussed, everything is charge based. Right? Charge current is flowing. And you know that if there is a current flow means a power loss, I square R. Right? So current means always there is power loss, I square R. So now if we think about a device and if there is no power loss, then it will be extremely important. So first thing we have to do, we have to stop the current flow, right? So that is in principle possible. So here we have used 2 inputs, say VA and VB, for 2 different charges, 2 different signals. Now instead of this, if we use say up and down spin of electrons to define spin states, so then this configuration means say input 1 and or on state, and this means your off state. As simple as that. Just we have to define two different states. So now if we design a circuit where everything is spin based, so that means there is no effective charge flow, and that is also possible to get spin based logic gates. So this is a simple schematic setup. Oh, it's already reference disappears. Okay, this is our recent one. Fine, no problem. So this is experimental setup. Also, the last 2 years. So everything is spin based. You can get all possible. Say this is NOR, XOR, XNOR, and all possible logical operations are there. And now, along with this logical operation, if you can also store the data. That means if you implement a storage mechanism, then it will be extremely important. In the conventional case, we have to add another instrument for this conversion, for storage mechanism, right? But in this setup, we can also store the data. This is the experimental principle there. So logical operation as well as storage mechanism, and extremely it will operate in less power because there is no physical movement of charged particles, right? So just on and off state, flipping one up spin and down spin. But the point is that if you work with this model or say spin system, then you have to flip one spin from say up or down. So you have to implement some mechanism so that you can flip the spin. So by applying magnetic field, as simple as that, you can rotate spin. But care should be taken that you have to apply magnetic field in such a way that other parts of the device will not be disturbed. Suppose I want to spin here in this way, and say if we apply a magnetic field such that other parts of the device are disturbed, so that will be not the ideal practice. So the thing is that you have to apply magnetic field locally so that other parts of the device will not be disturbed. Okay, so that is the important thing that we have to do. Okay, now so far we discussed, it's based on some normal metal, or you can think about also semiconducting material. Now people are trying to think that can we replace all these nanoscale conventional materials by molecules, right? That will be much more efficient and more stable. So the question is, can we replace the bridging materials with molecules? Okay? So suppose I just want to replace this bridging materials means this one, that bridges source and drain electrons by molecular system. And the answer is of course yes, it is possible. In 1974, two famous scientists, Oviram and Ratner, they first proposed that yes, it is possible. No, I have already, I have already sufficient. No problem. So, this is the first theoretical proposal, theoretical work. Okay, in 1974 by two famous physicists, Oviram and Ratner, published in Chemical Physics Letters, they consider a simple benzene molecule, right? And see, there are two electrodes by yellow colors. Normally in experiment they consider gold. And there are another two atoms here and there. This is basically sulfur atom. So you cannot just attach the benzene molecule directly with the electrodes. So you have to consider thiol group. Thiol group means SH bond. In the chemisorption technique where hydrogen atom should be pacivated, so sulfur atom will reside. So that means this gold electrode, then sulfur, then benzene, then gold, then sulfur, then gold. And They have shown that, okay, it is possible, we can think about a molecular system. But you can imagine how small it is, right? Just benzene, 6 carbon sites. So, okay, it is fine, you can do whatever in theory, but it's really possible to design it experimentally. So experimental results, it took a little longer time to get it feasible. In 1997, so theoretical paper was in 1974, it is in 1997 by Mark Reed and his group. They first able to measure current to the same benzene molecule, current as a function of bias voltage. So in 1997. Okay, so that means both theoretically and experimentally it's possible to measure the current, and after these works, there are several works going on and several propositions have already been implemented in the molecular system. So people are trying to replace all the conventional material by molecular systems. Just I want to highlight some important aspects along this line one by one. See, you are familiar with the transistor, right? Conventional semiconducting transistor. Now you see that simple benzene molecule which was published in Nano Letters. There are 3 electrodes, right? So you have a molecular system like this and 3 electrodes. And the important thing is that your conventional biasing is not required, but you have already read that collector should be much bigger in area compared to base, then emitter, and so many things. But in that particular case, not so much conventional biasing is required. Very simple and it's very stable. So it is one breakthrough in this area that transistor can be designed using simple benzene molecule. Nowadays people are considering different other complicated molecular system. I'll come to that one by one. But this is a simple one where you can in principle design a transistor. Now, this is another breakthrough one in this area. This is not so old, 2011. Okay. Weizmann Institute people, they have done this experiment. This is really interesting. They have measured spin polarized current. What is the meaning of spin polarization? The simple thing is that suppose you have unpolarized beams, means 50%, suppose you have up spin electrons plus 50% down spin electrons, right? In the right end, I want to get either up or down. That means it will be polarized. And earlier, people were using ferromagnetic material. You know the meaning of ferromagnetic material? Suppose you have a ferromagnetic sample like this, where you have finite magnetic moment like this. Now if you inject unpolarized beam of electrons here, you will get polarized beam. What is the basic principle? So you are injecting unpolarized beam in this side. Now, since all the moments are aligned in a particular direction, if you calculate the energy spectrum for up and down, means allowed energy band, you will see, this is of course the schematic diagram. So up to this is the allowed band for up spin, and this is the allowed band for down spin, right? And this is overlap region, okay? Now this overlap region essentially depends on the strength of the magnetic moments, right? So now, up to this region, you will get only up spin electron, right? Because this is the band of up spin. And for this region, you will get only down spin. And this is the mixed phase zone. Both up and down spin will pass through this. So now, if you set the Fermi energy of the sample within anywhere this region, definitely you will get up spin. That is not an issue. But the point is that this is your, say, equal to 0 line. And it is very hard to set Fermi energy far below this line experimentally. You have to think about experimental situation also. So if you want to set Fermi energy here, okay, theoretically it is very good. It sounds nice that okay, we can get only up spin, but practically in actual situation, it's very hard to set Fermi energy at this far end of this line. So people are using this ferromagnetic material normally for this spin polarization, but this is not usually not a good practice for this. Because in that case, essentially you don't have any tuning parameter. So once you have a specific ferromagnetic material, means your this band structure is fixed, you will get the response. But if you want to tune it externally, it's always important for designing an efficient device, that is not possible. This group, they have shown that instead of ferromagnetic material, if you take helical molecule, this is very simple to access. Say for example DNA molecule or say a protein-like molecule, right? Now you know the structure, say this is one helical molecule and say you can think about this one, this single stranded, you can also think about double stranded DNA. Now there are two examples, say one is alpha helical protein and say single stranded DNA. Structurally you cannot distinguish them. Structurally both are helical, both are same, but result wise completely different. They took such a helical molecule and then they consider a gold substrate here, this is gold, and applied light in it. So if you inject light, it will emit 40 electrons. So you have equal probability of getting up and down spin electron, fine. What they observed that, so in this end, both up and down spin, that means this one, these two color. And at the other end, you will see only up spin in one case, and other case, it will be down, depending on the helicity. And till now, this is the highest reported rectification ratio they have shown using DNA molecule. The maximum polarization can be achieved by using this DNA. But theoretically, it is really very complicated because you have to incorporate this helicity effect in your calculation. This is not as simple as that, like other case. So this is one example that considering DNA molecules, you can get polarized spin current. Okay. Now, again, this is another interesting thing that by considering this DNA molecule, the rectification is also possible. And this is very recent work. So what is the basic principle of rectification? So current should be different under two bias polarities, right? So that means if you reverse the bias, the current should be different. And it is very hard to get in a normal molecular case, right? If you have a simple molecular system or a simple conductor, you will always see that the behavior will be like this, so it will be like this. The magnitude is always same, normal case. But if you consider a DNA molecule and under certain condition you can show that a high degree of rectification can be achieved even at too low bias. Let's say, for example, 0.2 bias voltage, 0.2 volt, you can get a very high degree of rectification. So this is the experimental work published here. This is another important aspect of utilizing molecule. And I want to highlight this one also. So molecular switch. You are familiar with this molecule, this is a biphenyl one. Right? That means two phenyl rings. Now, what is happening here, when the two phenyl rings are in the same plane like this, you will get maximum conductance. And now, if you rotate one molecular ring with respect to other, the conductance will gradually decrease. And when one phenyl ring is exactly perpendicular with respect to other, conductance will exactly drops to zero. So no electron can transfer from this side to that side. And if you plot the conductance, say, as a function of this twisting angle, you will see it should be pi by 2. So that means tuning this angle or rotating one phenyl ring with respect to other, you can eventually regulate your conductance from this maximum value to this minimum. So this is your off state, right? This is your on state, but in between also you can get different values of conductance. So basically you can tune the conductance. It was published in Nature. Experimental work. So in all aspects you can see that molecular systems are very, very important in designing devices. Okay. Now come to the other parts. Normally whenever we do any experiment, we measure always the final response, means transport current and the drainage, right? So if we say do an experiment for IV, then we calculate current I for different voltage at the right end, means the response of the full sample, right? That is called transport current. But along with this transport current, there is a possibility to get current inside the loops if you have a geometry having single or multiple loops. So this is our total current which is coming from this, and we are familiar with this one, this total current. And we normally in experiment we measure this one, right? So for the bulk case we just use the ammeter and then we calculate this one for different voltage. Okay, that is fine, but along with this total current, we can also get some finite currents inside the loops depending on the situation, on physical condition. And the thing is that due to this current, a magnetic field will be established, as simple as that. If you have a current in a loop, it will produce a magnetic field. And here I have not applied any magnetic field externally, right? There is no solenoid, nothing. So this magnetic field is established because of this transport current under certain condition. And if you calculate this magnetic field, you can see that it will be of the order of some Tesla, because the area is very small. If you have a bigger ring, it will be small, the magnetic field will be small. But if you have a very small ring, the magnetic field will be very large, because you can imagine the area of this ring. And this magnetic field can be utilized in different ways to get selective spin transmission and many other things. This is one proposal along this line. So what they have shown that if you place a magnetic site there, then you can tune its orientation by that magnetic field also. So basically with this you will get selective spin transmission just by changing either the direction of this or by changing the strength of magnetic field. Okay, fine. So our main motivation is that how to control local magnetic field in a narrow junction, because if we think about say spin based logic device or any other, we need to tune the magnetic field locally so that other parts are not disturbed. Okay. There are few propositions along this line. This is the first one, that if you have an infrared laser pulse in an isolated quantum ring, suppose you have a quantum ring like this and you have irradiated this, okay? So you have injected light. In presence of this light, a circular current will be established in that, right? And that circular current will produce a magnetic field. And if you tune the strength of this, means if you change the intensity, you can also regulate this magnetic field. This is one proposition along this line. If you take a nano ring and if you irradiate it with light, you will get circular current. And then another proposition, this is an infinite area of parallel current carrying waves, but there is many limitations. Basically, if you increase the temperature, it almost disappears. So it will work maximum 10 millikelvin or even less than that. And the another option that if you connect a quantum ring with quantum wire, and by applying some in-plane electric field you can regulate the local magnetic field. This is another option by changing molecular conformation, but what I want to address here is by regulating quantum interference. This is a new proposal. So what is the schematic diagram? This one. So we have the benzene molecule and it is connected with source and drain electrodes. Now there are, so this is TS, means this is the coupling of coupling between the source and this side on this molecular ring, and this is the conventional case. Now due to the close proximity of these two electrodes, that means this one and that one, there is another coupling. So we are familiar with this one. Suppose we have a molecule, right, and say this is your source and say this is your drain, right? We are familiar with this. But if you couple this drain in ortho configuration like this, this is an ortho configuration, and since these two atoms are close enough, in addition to these two couplings, that means this one and that one, there will be additional coupling, right? This TC, this one. So you can regulate it just by changing the positions of these, even by changing the orientation. So there are three possible paths. So electron can come from this, it will go directly through this and it will reach to that path. There is another possibility is that this one and this is the last one, TC. So you have one tuning parameter here, TC. You can regulate it. And here I will show you how to tune magnetic field. Okay, now I will skip all the theoretical parts because this part is quite complicated. I will always come to the results. Yeah. See, for this setup, it is the in this axis is the transmission probability and as a function of energy, and this is the result of say circular current as a function of voltage. Okay, so just to describe this, I want to address this one. Suppose you have some allowed channels like this, and you have connected it with source, and this is your drain. And I want to calculate current. So what is the prescription? So electrons are coming from this end, it will eventually reach to the other end. Okay. Now whenever the energy of the incoming electron matches with any one of these allowed channel, you will get a finite transmission. So if I plot transmission as a function of energy of the ejecting electron, then you will see that, say, if your energy is same with this one, you will get one peak, right? So that means you will get different such peaks associated with the energy spectrum. So essentially, this transmission energy spectrum manifests itself the allowed eigenvalues of the bridging material. Now, these are some resonant peaks, and this is the variation of current. Normally, if you have a small scale system, if you calculate current, you will get the behavior like this, step-like behavior, right? But in the case of ohmic material, you know, it is simply like this. So what is the basic difference between these two? Actually, in this case, if you want to calculate current, you have to follow the prescription. Just I will write one simple equation. So current I as a function of voltage, it can be written as 2E by H times your transmission function times F. This is say F minus E by 2 to F plus V by 2. So you have to integrate the transmission function. And you have such discrete transmission peaks. So now, in absence of any bias, there will be no current. That is fine. But if you apply a finite bias, and suppose your bias is like this is your bias window, and still there is no energy channel is there. You cannot get any current. And if you increase this window, suppose you have one energy channel comes in this window, so you will get a finite current. And if you increase more and more, so you will get this step-like behavior. So why we are getting this step-like behavior? This is basically due to this fact, this resonant peaks is very sharp and it is not continuous. Clear? So what we get that if we increase the bias window, more and more number of energy channels are coming within that window. So always current should increase. It will not decrease if we not apply anything externally. So that means you will add more and more number of contributing energy channels. So current will always increase. And see here it is always increasing. This is the transport current. Fine? But for the case of circular current, the scenery is not like that. It can be positive, it can be negative as well. So what is the definition of circular current? So you have a simple geometry like this, and you have attached source and drain. And say in this arm the current is I1 and this arm current is I2. Okay? Now definition is very simple. Circular current, this is I1 L1 plus I2 L2 by L1 plus L2. As simple as that. L1 and L2 are the lengths of upper L1 arms. Right? And if it is connected symmetrically, so under this situation your L1 equal to L2 equal to say some constant L0, and then your I1 will be equal to minus I2 equal to say some I prime, because the current in the upper and lower arm will exactly same but opposite in direction. So in that case you cannot get any circular current. Right? It will actually cancel with each other. So to get circular current you have to break the symmetry. So that's why if you have the geometry like this, so for our case, this benzene molecule, if you connect source and drain like this, that's para configuration, you cannot get any circular current. Because lengthwise both upper and lower arms are symmetric. So first you have to break the symmetry. Right? Now, when there is only one energy channel, suppose you get a current along this direction, and if you increase the window, another energy channel may come, and for that, say current is propagating in this way, so they will mutually cancel. So that's why in the case of circular current you can get both positive current as well as negative, right? And if all those energy levels, means contributing energy levels, cancel each other, you will not get any response. So here you can see that up to this there is no circular current, but now it's negative, and then again it is in this way, and here I can see that this current of the order of, I think it's milliampere, and now if you calculate the associated magnetic field, you see this is the 9.2 of the order of Tesla, very large magnetic field because the area is very small. And if you place a local spin here, and if you want to rotate it, the required magnetic field just 7 millitesla. And here, you see, very large magnetic field, because area is very small. So there is enough possibility to do this. And now, in our setup, we have additional coupling TC here, and that we can tune externally. Okay, so by tuning this TC, I think this one is TC. Yes, so this last one, we have changing the TC from 0 to say 1. You see a wide change of this 0.2 to this one. That means it is almost -1 Tesla to +1 Tesla, just by tuning this TC. Okay, and so you can also think about, say, for other bigger molecules having multiple loops, and also will get circular currents and magnetic field in each of these loops, and you can tune in principle by regulating the coupling between source and drain. So there are some results. In all the cases we see that, so for different 5 loops, you can regulate magnetic field in a wide range, and important thing is that here we have said very small bias voltage, that means 0.2 or say 0.3 or 0.5 like that. So important thing is that there is a certain possibility to regulate the magnetic field, that means the circular current induced magnetic field. There is no external magnetic field, and that magnetic field can be utilized to get selective stream transmission or say many ways. So what I can say that a new proposal is given to control local magnetic field in a molecular junction. So locally you can tune magnetic field without disturbing other parts of the system. That is one important thing. And this analysis may provide the possibility. So by using this principle, you can effectively get selective spin transmission. That means in that case you have to place a local spin there, and considering the interaction of that local spin with the applied magnetic field that will be established because of the circular current. So it will indicate the emergence of molecular spintronics, and what is your ultimate goal, that effective design of a system. Thing is that we want to regulate this magnetic field or circular current externally without disturbing any physical parameters of the system externally, either by applying electric field or by, say, for example here what I have discussed already when tuning this DC, and for using single spin quantum logic, that means we can do computation with single electron spin. Okay, that's all. And so now feel free to ask me if you have any question. Yes.
As you have shown benzene ring between 2 electrodes.
Yes.
Is it ever possible a current? I mean, all the electrons are locked within bonds. So how can a current flow through such a molecule?
No. So you are asking that if you have a single benzene molecule, suppose this one,
Yeah.
right? This
It's a
one.
benzene molecule. So all the electrons are locked within bonds. So how can a current flow?
How is it locked within bonds?
I mean, covalent bonds.
Why it is locked?
Electrons can move from one bond to other.
Of course.
In the resonance,
Definitely it is possible. And I have already started with the theoretical proposal with benzene molecule. That is the first one, but they have already shown. That is possible.
So his question is probably whether there are free electrons to carry the current.
No, actually these electrons are coming from the, I have connected it with this source and drain. It is not the isolated one, right? I have not considered only this one. Okay? So electrons are coming this, it will see some potentials here and then it will transmit. Okay, that's very simple, no problem. I'm not considering simple isolated ring. Okay. Here it is connected with source and drain electrons. So electrons are coming from the left end, and then it will eventually transmit. And whether it will transmit or not, it depends on the quantum interference or different effects. Say for example, what I have already discussed, if you apply a magnetic field here, and if you set it say phi 0 by 2, then due to complete destructive interference, no electron will transfer from this end to that end. And another thing is that, say for example, you connect source and drain in this way. This is your para configuration, right? So you will get one kind of response. Now if you move this one here, there is a meta configuration. It will drastically change because of this quantum interference. Because you see that the path length is this, here this one. And now for the other configuration, ortho configuration, it will be again different.
Sir,
Yeah.
যে প্রথমে ওয়ান ডাইমেনশনাল একটা চ্যানেলের মধ্যে দিয়ে
হ্যাঁ।
সোর্স থেকে ড্রেনের দিকে যাচ্ছিল, সেখানে একটা রেজিস্ট্যান্সটা কনস্ট্যান্ট দেখালেন, একটা এটা কি যে কোনো লেন্থের জন্য কনস্ট্যান্ট?
হ্যাঁ, আমি ওই এক্সাম্পলটা যেটা দিয়েছিলাম এরকম, single mode energy channel, right, and connected with say this source and this drain, and I have already mentioned the term that is the ballistic channel. Okay, ballistic channel means if you take say 1 centimeter or 1 meter, it doesn't make any difference. But to define a mesoscale system, what I mentioned that we have to consider the sample size within those length scale, comparable to those length scale. One important length scale I already mentioned, that is phase coherence length L phi, and for one dimensional case it is inversely proportional to this one. So when can we expect this one? The basic statement is that the average level spacing delta E, it should be greater than your thermal energy kBT. So if you have say only one atom, right, just like quantum dot, you know that discrete energy levels are there. Now if you have say 10 atoms, definitely the level spacing will be less. The thing is that you have to restrict this condition delta E, that is the average spacing. Okay, so suppose you have these energy channels. Here delta, average delta E, say for example this one, it should be greater than this thermal energy. Now if you take say 1000 atoms, then you know that many energy levels will come there. So that means you have to reduce your temperature. As simple as that. So that's why there is no strict definition of mesoscopic regime. Right? So if we reduce the temperature, L phi will increase. And mathematically if T equal to 0, L phi will be infinite. So in that case you will see. But practical situation means there is always some finite temperature. Okay? So this is the condition, means to observe mesoscopic phenomena, you have to apply this condition that thermal energy kBT and spacing delta E should be restricted by this. Delta E should be greater than this. Okay. And anything else?
Sir, when the normal metallic ring, an infinite similar thing, how can the current persist? Unlike superconductors, like we know that.
Oh, that I already discussed. So if you have a ring, small means how much dimension about which you are?
No, usual, but its thickness when it's made infinite.
No, first experiment was done on a square lattice, on a square loop. So the first experiment was done on this geometry because that time it was not possible to construct a ring, and the dimension was this 1.2 micrometer. It's copper, the concept copper. It was done by Levy and his group. So you can imagine the dimension of this. But the point is that to get persistent current or non-decaying circular current, because this is a normal metal, not superconductor, right? So normal metal means there is only free electrons, the charge carrier. So the condition is that the length, the circumference of the ring, it should be small compared to the coherence length, L phi. Okay, so this is the most fundamental statement.
Coherence length of what?
Yeah, coherence length of, no, electronic coherence length. And I already mentioned that this coherence length is inversely proportional to temperature. So if you reduce the temperature, your length will be large, so that you can take bigger ring. Fine? And another important thing is that here, say for example, circuit current is established, but how to measure that current? You cannot connect an ammeter there, because, right? So you cannot get any current there. So how to measure this current?
Magnetic field strength.
No. No, normally, experimentally, normally they measure magnetization. And you know magnetization means current loop area. Huh? So magnetization can be measured quite easily by using this instrument. In all research lab you will find this. Squid. So they can measure magnetization. But nowadays they are not measuring this magnetization. Some they calculate this current by measuring specific heat. And another recent proposal has come, it is cantilever technique. So now there are several other proposals. But earlier, initially it was measured by squid. So they measure magnetization and you know the loop area. So you can calculate current. And current of course very small, of the order of say microampere. But apparently it seems that it's very small. But actually it is not very small because loop area is very small. So once it is established, because of this small area, the magnetic field that will be generated will be very large. So in that sense, it is not so small. Okay, that is the point. And the lowest possible ring that was designed, just considering 10 atoms. So these are the 10 atoms. This is the lowest reported. Just considering 10 atoms, they can construct a ring. Just by triggering atoms. And in nanolithography technique, there are several other techniques that I don't know. So it is the lowest possible ring size, considering 10 atoms.
Another thing that you said, the dimensions of the ring should be much less than the coherence length.
Yes.
I mean the coherence length of the electron waves.
Yes.
Like
Yes.
wave particles when it is.
Yes, electronic coherence length, of course. Because this is a quantum mechanical phenomenon, right? And for 1D you can show that it is roughly proportional to 1 by T. Then there are different mechanisms for which this coherence length gets destroyed. One is electron-electron interaction, electron-phonon interaction. So there are many. So if you are within this coherent regime, then you can expect this phenomenon. And this is a direct consequence of Arnold effect. So where conductance oscillates as a function of this flux phi. It is no longer constant.
So you said that a destructive interference, is there some kind of electron-electron interaction like
No, there is no, I have not considered any electron-electron interaction. This is normal independent electron picture. You can consider individual electron-electron, so Coulomb interaction. But here I already, what I discussed, it is completely free electron picture. No interaction is there. So as source and drain are connected in such a way, the upper and lower arms are symmetrical. And you know the expression, cosine of 2i pi phi by phi 0. So if you set phi equal to phi 0 by 2 cosine pi minus 1, it will cancel actually g0 minus g0, that means 0. That's why destructive interference. So it will be oscillating.
So what are you calling it? Interference. When the interference comes in when...
Yes, so it's very simple formula that to get electron in the right end, so you have to write this one, psi 1 plus psi 2 mod square. This is basically this one. So conductance is proportional to this one. So lengthwise symmetric. So if you have psi 1 square plus psi 2 square plus psi 1 star psi 2 plus psi 2 star psi 1. So that's why it is g0 plus g0 times cosine twice pi phi by phi 0. And this expression is valid for symmetrically connected junctions. So if you change the symmetry, it will be something different. And say for phi equal to phi 0 by 2, it will be g0 minus g0. So cancel out destructive interference. Okay.
Sir, is there any role of plus I minus I or plus I minus resonance or inductive effects in this conduction through benzene ring?
Plus?
Inductive effects.
Oh, self-inductive effect, something like that means you are suggesting that say if one's current is established, it will produce a magnetic field that will again affect the current?
No, means this is a term of chemistry. While you are pushing electrons through any bond, so that is pushed into that current, that is the electron cloud of
means you are talking about say electron-electron repulsive?
Repulsive means electronic interactions.
If you are asking that whether electron-electron interaction effect will play an important role or?
No, in that physics is induction and chemistry induction. So electronic induction I am talking about.
I'm not getting the point properly, but what I want to say that, say for example, for the case of persistent current, I already mentioned that if current is established, it will persist, and because of that current, another magnetic field will be established, right? So you can think of, okay, that magnetic field will again disturb that current. So you have to do it self-consistently. Eventually you will see that you will not get any different kind compared to this, because that self-inductive effect will be very small in that particular case. But I don't know what you are asking. But if you include electron-electron interaction, that will be something different. That is many body problem, and you will get something else. This is the non-interacting method. Okay. And it is also very hard to do interacting system, because you cannot do it exactly. You have to either use many body field or something else. Okay. Oh, আচ্ছা আচ্ছা, তাহলে দেরি হয়ে গেছে, পরে বলছি।
বাপিদা,
We will now proceed on to the second part, and we will have technical session 2, which will be chaired by Professor Arnav Das, and we will also have 3 speakers. For now, it is Dr. Amit Trivedi, Sushil Kar College, and he will speak upon the title AFM Mobilus Wheels, a novel frustrated quantum system.
So anyway, you have to
Thank you. Really good afternoon to all of you. First, I'd like to thank the organizers, especially Rajesh sir, for inviting me to be a part of this wonderful conference. As you can see, I'll be talking on antiferromagnetic Mobius wheels, a novel frustrated quantum system. Let's start with a very simple thing. I'm sure you have done this in your school days. Mobius strip, named after this German mathematician. It's very easy to make a Mobius strip. You take a strip of paper, and instead of connecting like this, you have to twist at one end and then connect it like this. It looks simple, but it has very interesting properties. Firstly, in topological language, it is said to be unorientable. That is, if you draw a perpendicular at one point and move around the strip, after a full rotation, you don't come back to the same point. You reach at the other end of the other side of the strip, so that your perpendicular points in the opposite direction. And there are a number of other properties also. You can check this. You can make this in your. It's very easy. One can generalize the idea of this strip to Mobius ladders. You take a ladder and then give a half twist on one end and connect it like this. That forms a Mobius ladder. Now this is a Mobius ladder. The ladder has ladder has 2 parts. Rung, these are the rungs, and these are the rail bonds. So So you can see there is 1, 2, 3, 16 bodies are making bonds with each other, and here is the twist of the Mobius ladder. So you can go to another structure by simply rearranging the bonds. That structure
Rearranging means without any topological change.
Without any topological change. So this structure and the previous structure is said to be homomorphic. The another thing is you can classify Mobius ladders into two classes. First one, if you take, for example, this structure, you can divide the whole system into two partitions. The first one here, I have taken V1, V3 and V5 here, and named it subsystems A, and another 3 here subsystem B. The interesting thing is that the members of the subsystem A doesn't interact with each other. They only interact with the members of the other subsystem. So this is the bipartite graph. But this is only possible if you take a Mobius wheel which has number of interacting bodies which is not a multiple of 4. Here there are 6 particles interacting with each other. But if you take 4, 8, 16, then you cannot make it a bipartition of that system. So this is only possible when the number is a multiple of 2 but not a multiple of 4. This is the class of Mobius wheel. These members are bipartite, where the number of particles interacting are not a multiple of 4. Now let's go over to the idea of molecular magnets. This is very interesting because here the bulk of the system, studying bulk means studying single molecule. This is particularly important because where if you take a very large system and your Hamiltonian has a very large dimension, then exact calculations not possible. But there are physical systems where the whole system, the bulk can be approximated as a collection of small clusters or plaquettes like this. And you study one plaquette, then you are basically studying the bulk of the matter. Another nice thing about this that there have been experiments where qubits, quantum bits has been encoded in this system. This is termed as zero-dimensional system. And what is frustration? The frustration, idea of frustration is very fascinating. This is the simplest example of frustration. This is the Ising model. The 3 spins are interacting with each other. If this is the Hamiltonian, now if the interaction is ferromagnetic, there is no problem because you can make all the bonds parallel to each other so that the total energy is minimized. But in case of antiferromagnetic interactions, you cannot make all the 3 bonds antiferromagnetic or anti-aligning with each other. You see, these 2 are anti-parallel to each other, but the third spin, it doesn't know whether to align with this or anti-align with this. So this is the basic example of frustration. One can generalize the idea of these 3 spins to any number of any ring with odd number of spins. Here, this is the experimental ring, chromium and nickel, where the interaction is antiferromagnetic, and because of the odd number of spins interacting in this molecule, there is frustration. These competing interactions, they forbid the long-range ordering, it prevents long-range ordering, and it makes the classical ground state degenerate because there is a number of configurations possible. and there is no one configuration which can minimize the global energy of the system. Now go back to our family of Mobius ladders. This is the first member of the family which is frustrated, which is non-bipartite. Because the number of spins interacting is 4. Here, this non-bipartite Mobius wheel is frustrated because you can see you cannot make, if the interaction is antiferromagnetic, you cannot make all the bonds antiparallel to each other. So the conclusion is that in the family of Mobius ladders or wheels, the ones which are non-bipartite are frustrated, and the ones which are not, which are bipartite, they are not frustrated. This is the last idea. Then I go to my work. This is I've been already mentioned in the previous talks. Entanglement. This thing is possible only in our quantum world, because in our quantum world you can write this kind of states where this is known as EPR state. This is the state of two spins, two spin-ups, which is essentially superposition of two classical states. The nice thing about is that if you measure one spin, the measurement affects the other spin. The general definition is like this: if the composite state of the system cannot be written as the tensor product of the states of the individual subsystems, then it is said to be entangled. Though it is a little spooky, but it has been proven to be a resource for quantum information theoretical and quantum computational tasks. We need this resource to measure, manipulate, to make it usable. Now one can think of different types of quantum correlations. You can bipartite the system, you can divide the system into two subsystems, A and B, and then think about correlations between them, or you can divide the system into more than two subsystems, like here 3 subsystems, and you can think of correlations among the different partitions. This is a bipartite entanglement scenario, and this is multipartite scenario. Now, like Professor Das mentioned in this talk, that the bottlenecks of quantum computation, one of the bottlenecks is the scaling up of the system. You cannot make a large system where quantum coherence is persistent. Another bottleneck is the robustness of the quantumness of the system, because if you increase the temperature of the system, then the higher excited states, higher level states, those become accessible to the system, and the system ends up at a mixed state. This thermal mixing has a decohering effect, and at a certain temperature, the quantumness of the system is killed by the temperature. That temperature is called as the critical temperature. Now here is the idea of robustness. You take a state rho, which is pure, and mix another state with it by an amount T, and mix it such a way that the combined state becomes separable. Now the amount T that is needed to be mixed with the main state, which gives the quantumness of the system, is the measure of robustness. Because larger is the value of the T, the more you need to mix the system, the state with other states to kill its quantumness. So the bottleneck is to make robust quantum states. So here there is a scheme which this idea has been applied to the scheme. Consider the thermal state of the system. This is a thermal density matrix. We can divide into two parts. This is the ground state part, this is the ground state population, and this is the rest of the part. Here we are thinking that if we stay at 0 temperature, we are at the ground state of the system, and that's if the state is non-degenerate, then it is a pure state. We have full knowledge of the state. But if we increase the temperature, then the higher level states that get mixed with the ground state, and the quantumness gradually decreases. And at a certain temperature, the quantumness is killed by the thermal fluctuations. So one can measure by this scheme the value of temperature at which the quantumness present in the ground state of the system is killed by the thermal fluctuations. That temperature is termed as the threshold temperature or critical temperature. So the more is the critical temperature, the larger is the critical temperature, the more is the robust. The more robust is the system against thermal fluctuation. So what I have done is I have taken the second member of the frustrated wheel, Mobius wheels. You see there are 4 spins interacting with each other, and to compare result I have taken another system with the same dimensionality, 8 spins, but here there is no Mobius twist. So this is not frustrated and this is frustrated. These are the topologically equivalent structures. So this is the Hamiltonian. Here there is a antiferromagnetic exchange interaction term and external magnetic field term. The external magnetic field term is needed because we need a knob to tune the system, to tune the correlations present in the system. So and I have calculated the critical temperature at which the quantumness present in the ground state that is killed by the thermal fluctuations. And this is the result. You see for this known as torus link, this is the variation of the temperature, critical temperature with external magnetic field. This one is for the non-frustrated system, and this is for the frustrated Mobius system with same dimensionality. You can easily see the significant improvement in the value of TC, critical temperature, when we use the frustrated system instead of this non-frustrated one. It is the variation of the TC with the external magnetic field. So the bottom line is that frustration here is making a role to make the system more robust against the thermal fluctuations and also external magnetic field perturbations. So if one uses this kind of frustrated systems, then we can make robust quantum states which can be used in quantum computation and quantum information tasks. Thank you.
This session is open to questions. There is no question, but you answer questions. So, for a finite system, you see a sharp temperature where some parameter for robustness, whatever, goes to 0 sharply, or is it like a real pulse?
I have used an entanglement measure for that.
I know. So that measure goes to 0 sharply, even for a finite system.
Yes.
Could you have a plot for that?
Yeah.
So if there is no further question, let's thank the speaker once more. Our next speaker is Suruji Vihara College.
Hello.
Good afternoon everyone. Now I will talk on quantum chemical structure and plasmonic properties of a series of planar and quasi-planar AL13 plus cluster. First of all, point. First of all, we have to know what is metal nanocluster. Generally, metal nanocluster consists of a small number of atoms and its dimension less than 2 nanometer. So, some properties like electrical, thermal conductivity, reflectivity, mechanical ductility, these properties are partially absent in this type of nanocluster. So, what is the cause of this? Because of the delocalization of electron in the bulk metals. So, for this reason, we can use this property in nanoscale device, and this property depends upon the shape and size of this nanocluster. And these are the several uses of nanoclusters as leaching of water, hydrogen storage, magnetism, solid propellant rocket, catalyst, and ion absorption. So we only focus on aluminum nanocluster. This is the series of aluminum nanoclusters and already has been proposed by B.K. Rao and P. Jena at 1999. He showed that aluminum atom containing 2 to 5 atoms is in planar form, but when number of atoms increase from 5 to more, then the planarity of this cluster has been lost and it takes 3D in nature. Also, Al13 plus containing 13 number of aluminum atoms within bulk atom within this cluster is also in 3D form. And plasmonic properties have also been studied for this cluster. But it is strange that planar Al13 plus cluster exists, which already has been published by us at the Journal of Molecular Modeling in 2018. Generally, number of atoms increases, then the cluster turns into the 3D geometry instead of 2D geometry. Why? Because instability of this cluster increases rapidly. So, planar Al13 plus cluster containing 13 atoms is unprecedented. So, we calculated this planar Al13 plus cluster by using different basis set and different methods. Using some basis, using 6311 plus GDP basis set and B3 density functional theory, we can get this structure. But this structure is not true minima structure because it consists of 2 imaginary frequencies. To reduce this imaginary frequency to 0, we recalculate it with different basis set. And finally, we got this quasi-planar Al13 plus cluster, which is true minima structure and containing 0 imaginary frequency. So there may be some intermediate structure which contain imaginary frequency 1. This is the transition structure connecting to this structure. So what is the geometrical property of this cluster? Cluster have the bilateral symmetry along the vertical axis. We can see this figure. Along this axis, 3 clusters have bilateral symmetry. And these 2 clusters is named as C3 and C2 are like a flying bird, whose wings are upward for both clusters, but tails are downward for this cluster and tails are upward for this cluster, and their optimized energy value has been shown in this table. So this from this table we also can conclude that this is the true minima structure because it has the least energy value. We have calculated electrostatic potential map for these 3 clusters. First is on planar cluster, second is on transition structure, and last is the true minima structure. From this structure, we can show that this is the more electrically negative zone, and this is the positively electron zone, a positively charged zone. So dipole moment is aligned in this direction. But when the cluster got transformed in this cluster, then charge is redistributed and the charge is transferred. There is a charge transfer from the periphery to core region. Due to this charge transfer, the resultant electric dipole is reversed and they directed along this direction. But when this cluster got transformed in this cluster, then the direction remains same, but the value of this dipole moment is increased significantly. So also we have calculated delocalized orbitals for these three clusters. So this figure shows that for planar structure, delocalization is due to only pi electrons only. But for transition and quasi-planar structure, there is sigma contribution of sigma electron is also possesses. So we can conclude that these structures, quasi-planar and transition related to planar structure, is more aromatic in nature. And this is the nucleus independent chemical shift, which is usually known as NICS. In ppm unit has been fitted in this figure. We divide the cluster in subsequent triangles and we calculated the NICS value in centroid of this triangle, and this NICS value has been plotted in this bar diagram. This bar diagram shows that the ring number 6, this is this ring and this R6 and R6 star ring is more aromatic in nature because its NICS value is more than rather than other triangle. And it is also shown that the NICS value is increased from planar to quasi-planar transition. It can be shown that this green line is more than the before two lines. So from this calculation, we can conclude that aromaticity is increases from planar to quasi-planar transition. And it's another parameter for aromaticity. This is known as electron localization function and ELF. What is ELF? If iso value of this ELF runs from 0 to 0.7, this is taken as non-aromatic. But when it's from 0.7 to 1.0, this is aromatic in nature. We plotted this in 0.7 to more than 0.7. We can see this from this figure that for planar cluster, the island is split in 5 segments. But for non-planar true minima structure, the island is split in just 2 segments. So from this ELF study, we can also tell that between 2D structure, aromaticity increases from planar to quasi-planar or true minima structure. And this is, so planar to quasi-planar structure, aromaticity increases. And if we see this before 3 results, from electron delocalization and NICS or nuclear independent chemical shift and electron localization function, 3 calculation correlates nicely, and 3 result tells that when cluster got transformed from planar to quasi-planar, then aromaticity of this cluster increases. Now we focus on plasmonics. What is plasmonics and what is plasma resonance? We already know that it is a collective electronic excitation characterized as the oscillation of the electronic density caused by the restoring force created by the induced electromagnetic field. So what is resonance frequency? This resonance frequency means in which frequency this oscillation can occur in maximum amplitude. This frequency can be very much tuned by the size of the nanocluster. This is the UV visible spectrum of these 3 clusters. We have studied this, and we have studied time-dependent density functional theory, or usually known as TDDFT, and the figure shows that the collective electronic oscillations mostly occur in UV range, and it changes with energy as well as size of the cluster. We can see this result in tabulation form. This result shows that larger planar AL13 plus cluster with less optimized energy provides less electronic oscillations. Transition state AL13 plus cluster with moderate size and optimized energy provides moderate oscillations. And true minima, which is true minima global minima structure with least magnitude cluster provides greater electronic oscillation, and which absorption band is located around UV region. So what is the conclusion? We can conclude that we can tune this resonance frequency by changing the dimension of the cluster. From this result we can nicely conclude this one. And what is the application of plasmonic? These are three basic applications of plasmonic. Plasmonic can be applied in nanocell as cancer therapy, invisibility clock, and plasmon LED and quantum dots. So if we conclude this presentation, in brief, we can say that we have found interesting AL13 plus cluster which is in planar form. This study also shows that quasi-planar structure has the highest aromatic character. All clusters cause anti-aromatic island within aromatic sea, and plasmonic property shows plasmon band concentrated about 897 nanometer, 911 nanometer, and 850 nanometer. So this is in UV visible range. This value nicely systematically varies with the size of the cluster. This is more significant conclusion. And finally, thank you.
The session is open for questions. So there is no questions. Let's access to the last question. Our next speaker is Dr. Somnath Bhattacharya, Bharat Government College. So the topic I want to discuss here is time scales in the current relaxation for the first passage population in random register compounding network model. So the material or the system I'm interested in is the composite material. So composite material is basically it's a mixture of two kinds of materials. Suppose one is colored as red and another is colored as blue. So they have much different generalized susceptibility, but they are mixed in a random, morphologically they are mixed in a random fashion. So that's why if you are interested on the transport property through this material, then of course the connection from one end to the other end, suppose this one is this is connected with a lower busbar and the upper one is connected with a higher busbar, voltage V. So we want to study that what kind of current you get from this zone and this terminal to that terminal. So as the transport property is highly dependent, so as the transport property is highly dependent on the geometrical connections among the conducting elements. So there is a standard technique in statistical physics which is known as a percolation. So percolation technique is quite useful.
quantity that I am interested in the relaxation. So relaxation, I mean it is a behavior of the system during its passage from non-equilibrium to steady state. That means if you just connect the system to some battery outside, some external battery, then you will never get the current, the fixed current or steady current readily, instantaneously. You have to wait for some time. So I'm interested on that phenomena or the behavior of the system from after connecting the battery and then getting the steady value. So there are actually two kinds of relaxation we are interested in. They are called the divide relaxation, that is mostly seen for the linear system. So as you can understand, for the linear system, the change of some quantity is proportional with the quantity that I have shown here. So that gives you an exponential relaxation. This was first discovered by Divide, so that is known as a divide relaxation. So for divide relaxation, we generally, we can explain that, we can just feed the total response with a single exponential function with a single time scale. So that's why we say that the linear system always possesses a single time scale. But if you just make a system with so many linear systems, linearly coupled, means the linear superposition principle is valid there, then also you will get the bulk response. So individually they are linear and their coupling is also linear, their proportion is also linear. So the total system also behaves like a linear, single linear system. So for linear system, we generally get the exponential relaxation. So that is very popular. Everywhere in physics we are familiar with the linear kind of or exponential kind of relaxation. But there is also another kind of relaxation which is not exponential. So that belongs to different types of mathematical function like logarithmic, the power law, which doesn't have any scale. So we are very much interested about this kind of non-divide class of relaxation, because it will, the relaxation mechanism or relaxation behavior also tells you that what is happening inside the system. So mostly in percolation, the linear system is mimicked or it was modeled by a old model that is called the random register network model. The model is a discrete version of that continuum figure that I have shown the cartoon. So there are some, those red lines are different bonds. Those are the conducting channels. And only, some current or some response can go from one side to the other only via those red bonds. And the white ones that you can't see, those are the insulating bonds. That's why mostly the response is not going through that. So if you want to get some finite current from this terminal to that terminal, you have to only follow those red bonds. So, but all the red bonds, they are like ohmic conductors. Those are known as ohmic bonds. So that's why the whole system is a linear system, and it shows, if you just plot the conductance or resistance versus the voltage, it doesn't vary with the resistance, doesn't vary with the voltage, as well as that if you see the relaxation mechanism, you will find it's an exponential relaxation. But the model I am interested in is called the random register and tunneling network model. It's also a percolating model, but in addition to those red bonds, in this model, some new green bonds has been incorporated. Those green bonds are those bonds. Suppose, for an example, this is red bonds, ohmic bond. This is another red bonds, but there is no connection between them. But we will consider as if it is something like a dielectric breakdown. This is the initiation of the dielectric breakdown mechanism. Suppose I have some dielectric material here, I have some metallic material here, and some metallic material here. And in between I have a less conductive material, which is a dielectric material. So that's why there is a possibility. So those metal clusters are separated by some length scale. So there is a possibility of transport from here to here through some dielectric breakdown. So that kind of possibility is incorporated here. And not only that, these bonds, green bonds, those are known as tunneling bonds. So it's not like the quantum tunneling, it's a semi-classical tunneling, so the model is the semi-quantum. So in the sense that we'll only consider that before some threshold, microscopic threshold for this, it will not fire, but after that it will behave like a linear bond or linear resistor. So in principle I can say that there are two kinds of bonds. One bonds are originally the random resistor bonds, and some new kind of bonds is incorporated, but they have a threshold. So that is, so I said that there is a correlated random bonds, correlation in the position, and due to this microscopic threshold in the microscopic bonds, the behavior, the G is the conductance, so conductance versus voltage behavior, that also shows this type of nonlinearity. So you can understand if the voltage is quite small, if the voltage is very small, then none of these green bonds will fire. So mostly this will be an effective random resistor network. And if you just go to a very high voltage, then all the green bonds will fire. So that's why you will get two kinds of effective RRN in our RTN model. If the voltage is very low, none of the T bonds are active, none of the green bonds are active, and if you go to a very high voltage, then all the T bonds are active. So it is an effective RRN. So that's why one generally expects that for a very low voltage, the relaxation is purely exponential, and for a very high voltage, the relaxation is also purely exponential. So the interesting point is the in-between part, which is known as the sigmoidal region. To study the numerical way, the relaxation mechanism in RTN model in numerical way, we have to set some parameters. So G0 is the GO is the conductance, microscopic conductance for the ohmic bonds. GT is the microscopic conductance for the tunneling bonds. So we can understand that this, though both of them are linear bonds, but the tunneling bonds has 100 times higher resistance than the ohmic bond. So really it's not like an ohmic, it's not a metal, it's really a dielectric material. And also we have incorporated some capacitance here, capacitance in the sense that below that, if it doesn't fire, below that there is a possibility of displacement current, so that we also have incorporated here. So what we do, we just take this lattice, at each point we set some initial voltage configuration, means we solve everything in an iterative manner. So at every point we set some value of the microscopic voltage, and then microscopic voltage configuration. So at every point, suppose this is some I, some j, we set some microscopic voltage, at this point microscopic voltage, and then we impose a local continuity, means we just check that whether at this point, because there is a Kirchhoff's current law tells you that the total current looking at a point should be 0, so the total current we try to make it 0. But initially, as you can understand, it never becomes 0 for an arbitrary case. So that kind of imposition will lead to updating rule that we call as a Kirchhoff's dynamics in the lattice dynamics, and we solve the problem in the Gauss-Seidel method. So it's basically Gauss-Seidel is a very popular numerical method. So in a Gauss-Seidel method, we generally take this as an updating rule. And then we also look for the global continuity for the final steady state. If I find that suppose this is my last layer and this is my nth layer, and suppose this is my first layer, so I just calculate what is the current passing through this and what is the current passing through this. If the current in and current out are the difference is much smaller than our desired accuracy, we say that we have attained the steady state. So by this way we study the relaxation mechanism in the system, and the time when it gets steady, when this current becomes lower than some value, then we call that as a tau s. So this tau s is one of the time scales that is present in this relaxation mechanism. Long before, in 2005, so we first time published a paper which shows that this shows early stage power laws in the current dynamics. So at that time it was long before, and it was really good work, and we got very good referee report from there. Arnav is laughing, so he was there. So, but more than that, before we used to think that all the early stage relaxation regime that will show the double power laws, but actually you see that two kinds of power laws are there. First, the exponent of the power law is smaller and then greater and then smaller. So all kind of things is also seen in experiments. But after that, we also found that it's not always power law, not also two power laws. It may be one power law. So this we have shown one power law, which is initial, but still non-exponential. But interestingly, all the, irrespective of the initial part, all the latter part attains an exponential relaxation. So this is the peculiarity of the system. Some systems are linear system, they show exponential relaxation. Some systems are non-linear system, they show non-exponential relaxation. But this RFTN, this random register tunneling network model, shows an interesting phenomena where there is a reentrance of the linear mode after a non-linear behavior. So that fetched the interest of us. And not only that, only the two power laws. So some understanding that I have just covered here in the recent published paper. Relaxation of the bulk current shows two distinct regimes in the sigmoidal regime of the current conductance voltage characteristics. A linear system like RRN shows an exponential relaxation for the entire duration, so it doesn't show, but it shows always. However, for the initial time, non-exponential regime vanishes for the upper linear regime and the lower linear regime. So if it is in the upper linear, means if it behaves like an effective random resistor network, you get an exponential relaxation. If it doesn't behave like that, you will never get like that. So which one is responsible? The responsible part is the tunneling bond, because tunneling bond is the extra inclusion that is there in the and it is not always there, because tunneling bond is always there in the dynamics. But after some time you get an exponential part, so that means after some time these tunneling bonds are there, but they are not working, they are not doing its expected action. So we said the transient participation of the T bonds is responsible for the non-divide relaxation. So that's why if we can understand, if we want to understand that how, what are the time scales present in the current relaxation in the RRTN, then one can also study that what is the behavior of these tunneling bonds during this dynamics. So maybe after some time the tunneling bonds become steady. So thereafter it is again an effective RRN, so that's why we get an exponential relaxation. So we did that. So we plotted the number. So we plotted the
Yes.
Sorry for the interruption from my part. So what we have done, we have just plotted the number of active tunneling bonds and then with time. So the upper one is the total number of active tunneling bonds. The lower one is possibly the horizontal number, means along the this is a vertical one, which is along the bus bar from the zero voltage, the zero bus bar to the maximum bus bar, and this is the horizontal one, means in a lateral direction. So mostly we focused on this, in this behavior, and it shows that there is a time after which the tunneling bonds becomes constant, the number of active tunneling bonds. And another thing is, this is the relaxation behavior. So we notice that approximately at 20,000 it gets saturated, and around 20,000 this behavior stops. So there are two regimes in the relaxation. First regime is a non-exponential. So that non-exponential regime is completely controlled. That is due to this is originated due to the fact that there are the changing number of the transient behavior of the number of active tunneling bonds. So we can identify this time scale, we say that tau t. Previously we identified another time scale which we said that is tau s. So these are the two time scales. These two time scales actually dictate what will be the duration of the total relaxation method. Now, so we identified, so as I just summed up, that there are two regimes: initial time non-exponential, latter time exponential, and around that tau t, total number of tunneling bonds saturates to a constant value, and tau s, the bulk current saturates to a steady value. So we cannot stop here. We have to do a statistics. What I have showed you before, that is true for a single configuration. But what happens for other configuration, for many configurations? So in our very limited resource in a college, I have just studied with 5,000 samples only, not much more than that. So with 5,000 samples, I have plotted that histogram of TT is basically tau t, and this is tau s, and this is the ratio. So they are the very well behaved ones, so they have a single mode, not exactly Gaussian, but okay, they have a single mode, so we can identify this is the most probable value. But if you take with different system sizes, they also vary. There is no much interesting things about that. So we are interested about what is the ratio. So whether these two are really linearly independent or they have some linear dependence. So we have plotted the histogram for the ratio. So for each of the samples, it's not that I have just divided this by this. For each of the samples, I have calculated what is the ratio, and then I have plotted the histogram. So this is for a particular sample, 41 by 41 sample. So in the next way, I have just done the same thing for different system sizes. So this is 20, this is 40, this is 60, this is 80. See, for all system sizes, and I have also done it for 120, so that I haven't shown it here. So what I did, so you see that for all system sizes, it behaves similarly, and if you increase the system size, then the histogram becomes narrower and narrower. So we had an intuition that whether this, for these modal values, probably it will saturate for a longer system, because you know that everything, we in statistical physics we deal all the system in a thermodynamic limit. So we adopted, so this is a table which shows that what are the different values. So we just plotted all the things, and we showed that actually it leads to, in a thermodynamic limit, it leads to a particular value which is 41.95, around 42. So that means, though there are two time scales, but interestingly both the time scales are not independent. Only one is independent, and if you know the ratio, then of course the other you can find out. So though there are two regimes in the system, in the behavior, But actually there is one dictating time scale. In 2007, in lecture notes in physics, edited by Pradeep Bhattacharya and Vikas Chakraborty, one paper came. It was done by Professor Ashok Sen and Shubhankar Majumdar from South Point School. They have identified another 2 time scales. But those 2 time scales, one of them is common with me and another time scale is different. But they have adopted a different route. So route is known as the first passage route. So what is that route? The route is the start after connecting the Aratian system between the external bias. So I said that when I have done the work, I have just presented here. So there I have started with initial voltage configuration, means random voltage at each point. They said no. We will start from a different, because for a relaxation study, for a nonlinear dynamics, it is also important where from you are studying. Because you have to show, you can show that there is a stable fixed point. So interesting point is this: if you start with a different initial voltage configuration, which is a typical voltage configuration which we say the breakdown mode, then what happens? And they have showed that in a breakdown mode they can identify another time scale which is known as tau b. They called it tau b. This is a time when you get a finite current. For my work, this is, still it's not published. I have just completed the work during maybe couple of weeks back. So I have just pointed out that what is the time. I have just calculated for different samples what is the time that the current is less than, up to the time the current is less than 10 to the minus 16. So there is a distinct breakdown. You start from a very small current, 10 to the power minus 320 numerically, minus 50, minus 50, minus 50, and then something like 10 to the power minus 10 or minus 16. 10 to the 5, like that. So it is sharp. It's not like adopting some Husserl-Koppelman mechanism and algorithm, but it's in an experimentalist way. I should say that where is the breakdown. So this route is through the dielectric breakdown. So previously we have identified, this was a new time scale identified before in 2007. So previously I have identified tau t and tau s. But now tau b has been identified before. But in my opinion, the tau b is not the proper time scale, because tau b can only be defined only for this type of route. If there is no dielectric breakdown, there is no time up to which, there is no finite current. So if you want to get some, if you don't, mimic some dielectric breakdown during the relaxation, you will never get tau b. But one can still identify the tau t and tau s for this kind of route also. So we can identify the tau b. So in that sense, I said that tau b is impractical in general. It gives me deep sorrow that I'm just criticizing my mentor. So then I went for the statistics of all of them, that whether there is any intercorrelation of them, as I've shown before. So this is I have plotted the tau t by tau b. So this is the ratio of the time for the t bond to get saturated and that the breakdown time, tau. So this is for 20, this is for 40. Again I did it for 60 and 80. Pretty good histogram. There is a light of hope. So I also did it for tau s and tau b. Tau s is the steady time and tau b is the breakdown time. So 3 time scales. Previously 2 time scales, tau t and tau b. And now for the new route, first passage route, there is another time scale, tau b. So 3 time scale, 2 ratios, 3C2. No, 3C2 is 3. Another time scale is there. So that I haven't shown. So so all the ratios. And then what I did, I have done some finite size analysis. So it clearly shows that there is a saturation. There is an indication of the saturation. Maybe I will work with 121 by 121, and I'm sure that I will get it. But for here, it's not very prominent. Maybe for a higher system, it will show. It will be observed. So I'm not very sure about this. So my conclusion will be like this. The Raratian relaxation shows two qualitatively distinct regimes. Their origins are different in origin and distinguishable in look. Origins are also different, and by looking at the relaxation mechanism you can show, relaxation profile you can show that up to which time there is a time, how to identify the time scale. They are having a distinct, effect in the relaxation profile. One may identify tau t and tau s as time scale, one of them is only independent. In the first passage problem, one may find a new time scale which is tau b. Our analysis shows that all of them are correlated in pairs. So though there are 3 time scale, but if there are all the ratios will lead to a fixed value, then again the same thing prevails. There is a single time scale. Now it's your choice that which one you will call as independent. Others I can tell you. Thank you very much.
Just say the session is open to questions.
Question maker.
One question. So what is the mechanism of this reentrance from
Actually, it's up to some time. Up to some time the tunneling bonds are active. Thereafter, they are active, but they are not changing with time, because you see that if you don't, if the number doesn't change, if they don't play, if they don't prevail with the on-off state, then you will never get a non-exponential. So when it stops doing or when it gets old, it is there. It's not. It hasn't died. If it is there still, but it's not non-functioning. It's not, if dynamic stops, then you get a pretty exponential, it's pretty linear.
So any other questions? So if not, it's successful.
So we have came to the end of our day-long seminar. Now, before ending this session, Mriganko Roy Bashuniya sir from our department will give the vote of thanks to our guests.
Honorable invited guests, teachers, and my dear students, it's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of the Physics Department, Ramakrishna Mission Vidyamandira, extend my thank you to the entrepreneurs of the seminar, principal, vice principal, and college committee. A big thank you to all the honorable speakers for their motivational speech. I must mention our deep sense of appreciation to Dr. A. Dash and S.K. Maiki for their inspirational speech. I also wish to express my gratitude to all my colleagues and co-workers. Without their constant support the program could not be done. Finally, I extend my pleasure and thanks to all my dear students for their cheerful and eagerness attendance, which makes this seminar is a successful.
So this is the end of this day-long seminar. There is some arrangement for some refreshments outside.